All right, so we're diving into some pretty dense stuff today, folks. Marcinkiewicz-Zygmund inequalities. Got a research paper here that's, well, it's packed with theorems and proofs.
It's a fascinating area, really. You can think about these inequalities like a sort of bridge, between the continuous world and the discrete world of math.
Right, because they're telling us, essentially, how much we can really learn about a function just from looking at its values, but just at a limited set of points.
Exactly. And it's all about how well we can capture the overall behavior, the essence of a function, without needing to know everything about it, at every single point.
So, like on page 1 here, we see the classic Marcinkiewicz-Zygmund inequality, and this one's for trigonometric polynomials, specifically in LP spaces.
Yeah, in equation 1.1, it just lays it all out there.
And what's striking, at least to me, is that it's showing us there's this equivalence between, the LP norm of our trigonometric polynomial and the LP norm of a function that's, well, it's basically just interpolating it at a specific set of points.
Yeah, it's basically saying if you choose your points carefully, you can get a really good approximation of how the entire function behaves just by looking at those points.
That's powerful stuff.
Oh, absolutely. In the paper, it goes beyond those familiar LP spaces. It starts looking at what's needed for these inequalities to work in more general spaces. Quasi-Banach spaces.
Quasi-Banach spaces. Those are a little less familiar, I'll admit. What makes them different, and why is the paper going there?
Well, the thing with LP spaces is they have that triangle inequality, right? But with quasi-Banach spaces, that doesn't always hold.
Making things trickier.
Definitely trickier, yeah. But way more interesting. They let us explore a wider variety of function classes. More diverse,
Okay, so expanding our toolbox. Got it. So what's next?
Well, on page 2, things get pretty interesting, I think. We get to theorem 2.1. And it basically says that if you've got a space that satisfies a certain kind of inequality, a Bernstein-type inequality, then you can actually find some pretty tight bounds on the maximum and minimum values of a function within certain intervals, that is.
Okay, hold on. Bernstein-type inequality. Could you unpack that a bit for me?
Sure. So it's basically putting a limit on how fast the derivative of a function can grow compared to the function itself, that is. And it's often expressed, especially when we're talking about polynomials, it's expressed in terms of the degree of that polynomial.
Okay, that makes sense. So if a space has this property, then theorem 2.1 tells us we get these bounds on how much the function can wiggle around within certain intervals, like in equation 2.3. But there's a catch, right? Remark 2.2 is talking about the size of the intervals and how that matters a lot.
You got it. You can't just make those intervals as big as you want and still expect those bounds to hold up. The paper uses the example of sin to make that point, actually. As n increases, that function, it oscillates faster and faster.
So the intervals where those bounds work, they have to shrink.
Exactly.
Interesting. Like try to, I don't know, like contain a wild animal. The more energetic it is, the smaller the space you can keep it in.
That's a great way to put it. And so the paper, it's really paying close attention to those kinds of constraints for different function classes, of course.
Got it. So on page 3, we hit theorem 2.6. This is where weighted Bernstein inequalities come in quasi-Banach spaces too. And there's this weight function, right?
Right. Equation 2.6 brings that in.
Okay, weighted Bernstein inequalities. That sounds, I don't know, kind of complex. What role is this weight function playing?
Well, it's especially important when we start talking about functions that aren't periodic, or when they're defined on bounded domains, because it lets us adjust that Bernstein-type inequality so we can better capture what's going on with functions that don't just neatly repeat or are confined to a specific interval.
So it's kind of like tailoring the inequality, making sure it fits just right.
Yeah. Like, think about algebraic polynomials, the ones we see in LP spaces. Those are defined on a finite interval, right? And they're not necessarily periodic. So the weight function, it helps us account for those specific qualities.
It's all starting to feel really intricate, I got to say. I'm definitely intrigued to see where this goes. What's next in our journey through this paper?
Well, on page 4, the paper dives into a really fundamental question. It's asking, how can we get away with using the fewest points possible, the absolute minimum, and still have those Marcinkiewicz-Zygmund inequalities hold true? And the answer, it turns out, lies in something called quadrature formulas.
Quadrature formulas, right? Those are the techniques we use to approximate integrals, right?
Exactly, using weighted sums. It's like a shortcut for integration.
Right, and theorem 3.1, that's where it lays out a whole framework for using these quadrature formulas, specifically for proving Marcinkiewicz-Zygmund's inequalities. but with the smallest possible set of nodes. So we're saying basically that if we find a good quadrature formula, one that approximates the integral of our function really well, then we can use those same points, the ones from the formula, and use those to build a really accurate representation of the function itself.
That's the idea. It's all about efficiency, finding the most elegant and economical way to represent a function, to capture its essence.
This is amazing stuff, really.
Yeah.
But I gotta admit, my brain's starting to feel a little full.
Yeah, let's take a break, come back refreshed and ready for more. Back again for more, huh?
Ready to jump back into those Marcinkiewicz-Zygmund inequalities.
You bet. My brain's recharged, ready for more math. We were about to tackle, I think it was generalized translation operators, pages 5 and 6, right? Right on. This is where things get a bit more abstract. The paper's looking at a different way to approach MZ inequalities, specifically in Orless spaces.
Orless spaces. I feel like I've heard of those, but could you refresh my memory a bit? What makes them so special?
Sure. So think of them like a generalization of the LP spaces we talked about earlier.
A generalization, so even more flexible.
Exactly. Orlick spaces, they give us a way to deal with functions that, might not fit neatly into those standard LP norms, because instead of just using a single power like the P in LP, they use a more general function to define the norm.
Okay, so more freedom, more room to maneuver. But how do these generalized translation operators fit into all of this?
Well, they give us a way to, shift or translate functions, but within these Orless spaces, of course, it's like in a normal function space, you might just shift a function by adding something to the input, right?
Right.
But with Orless spaces, you got to adapt that idea of shifting a bit, to fit the specific rules of the space.
Makes sense. You need a special tool for a special job. And theorem 3.3, that's where we see an example of how this all works, yeah.
Exactly. Theorem 3.3, it uses something called a de la Vallée-Poussin kernel, and of course some special properties of that generalized translation operator. It's a really neat way to get to those MZ inequalities, but coming at it from a different angle.
So we've got quadrature formulas on one side and these generalized translation operators on the other, like two paths leading to the same destination but through completely different landscapes.
That's a great way to put it. The variety is what makes this area of math so fascinating.
All right, onward. The paper then takes us back to some, I guess you could say, more familiar territory. Pages 7 through 9, we're back to trigonometric and algebraic polynomials.
Yep, back to basics, but with all these new tools and insights in hand. Theorem 4.1, for example, it's all about reconstructing those trigonometric polynomials. But we're doing it in certain Banach lattices, and we're only using their values at, a very specific and minimal set of points. Equidistant nodes, to be precise.
So connecting the dots, but in a very mathematically rigorous way, taking samples, but carefully chosen ones, and then using those to rebuild the whole function.
Exactly. And it's thanks to the MZ inequalities that we can pull this off using so few points. It's all about efficiency,
Yeah.
Precision.
And this isn't limited to just trigonometric polynomials, right? Theorem 4.4, that takes this idea even further. To Orless spaces, I think, but with some caveats. What are those restrictions and why are they needed?
You're right. Theorem 4.4 does generalize to Orless spaces, those more flexible spaces we were talking about. But to make sure this whole reconstruction thing still works, we need a few extra conditions on those Orless spaces.
What kind of conditions? What makes an Orless space suitable for this kind of reconstruction?
One of the big ones is a growth condition. It's tied to that defining function we talked about earlier. It's like this growth condition, it makes sure the Orless space has enough structure, for lack of a better term, to make the whole reconstruction process work. Without it, things could get too unpredictable.
Like building a house on, shifting sand. Gotta have a solid foundation.
Exactly. And those conditions, that's what they provide, a firm mathematical ground for these reconstruction techniques based on MZ inequalities, even in these more exotic Orless spaces.
This is all incredibly insightful, really starting to grasp just how deep these MZ inequalities go.
Yeah.
And how they connect so many different areas.
They're like a common thread running through so much of analysis.
This is making me really want to dig into those applications now. What's the paper got in store for us there?
Oh, the applications are where the true power shines. But before we jump into that, let's give ourselves a moment. Let all this settle in a bit, and then we'll tackle those applications head on.
Okay, so we've talked about the theory behind Marcinkiewicz-Zygmund inequalities, right? We've seen how they connect to all these different function spaces and how we can use them to rebuild functions, even from just a few carefully chosen points. But now I'm really curious about, the applications. How does all this theoretical stuff actually get used?
That's the best part. This last section of the paper, it's like a showcase. A whole bunch of really powerful applications of MZ inequalities.
Yeah, I saw it covers like error estimates for sampling operators, Nikolskii inequalities, Gulyanov inequalities, even stuff about embeddings of B-soft spaces. That's a lot to unpack.
It is, but each one shows us something different about just how versatile and powerful these inequalities are.
All right, let's start with those error estimates for sampling operators. What are those exactly? And how do MZ inequalities help us figure out how accurate they are?
Okay, so imagine you've got a continuous signal. Could be anything, like a sound wave or even an image. And a sampling operator, what it does is it takes snapshots of that signal at specific points. So you end up with a discrete representation.
Like digitizing an analog signal, right? Turning continuous wave into a bunch of ones and zeros.
Exactly. And the big question is, how well can we get back to that original signal from just those samples? And that's where the MZ inequalities come in.
So they give us a way to measure that error, the error that comes from sampling, which is like super important for anything digital.
Like, absolutely. Like theorem 7.1, that gives us an error estimate for, for Lagrange interpolation. It tells us the error is bounded by the best one-sided approximation of the function.
Whoa. Okay, hold up. What's a Lagrange interpolation polynomial? And what does that best one-sided approximation thing even mean?
So a Lagrange interpolation polynomial, it's basically a way to build a polynomial that goes through a specific set of points. It's a classic technique.
So like connecting the dots, but with a polynomial.
Exactly. Now, the best one-sided approximation, what that means is you're trying to find a function that's, well, it's always greater than or equal to your original function at those points. But overall, it's as close as possible to the original function.
So it's like finding a ceiling for our function. That touches all those sample points.
A ceiling. Yeah, that's a good way to think about it. And theorem 7.1, it tells us that the error in our Lagrange interpolation, it's no worse than the distance between that ceiling and the original function.
I see. And corollary 7.2, that extends this idea, right, to different ways of measuring how smooth a function is.
Right. It basically says the smoother your original function is, the better your reconstruction is going to be.
Makes sense. Like, if a function is all jagged and spiky, it's harder to get its shape right with just a few samples.
And the MZ inequalities, they give us the math to back that up.
Okay, so that's how MZ inequalities help with sampling operators. What about those Nikolskii inequalities? Those seem a bit more abstract.
Yeah, Nikolskii inequalities, they're about connecting the norms of a function, but in different spaces.
Norms. Remind me what those are again.
Oh, right. A norm, it's just a way to measure how big something is, like a vector or a function, like the absolute value for numbers, but more general.
Okay, so Nikolskii inequalities are linking how big a function is, but measured in different ways. Why is that useful?
Because different norms, they tell us different things about the function. Like one norm might be all about the average value, while another might focus on the maximum value. Nikolskii inequalities let us translate between those different perspectives.
That's neat. So theorem 7.3, that gives us a Nikolskii-type inequality for those trigonometric polynomials, specifically in a Banach lattice. What's that telling us about these polynomials?
It's saying the norm in a, let's say, stronger space. It can be bounded by the norm in a weaker space.
Stronger and weaker spaces. What does that even mean?
Think of it like a stronger space, the norm there, it's really sensitive to any changes in the function, while in a weaker space, the norm is more forgiving.
Okay, so theorem 7.3 is saying if a trigonometric polynomial behaves well in a more lenient space, it's also got to behave in a stricter space.
Exactly. And remark 7.4, that points out how this can apply to other functions too, even to quasi-Banach lattices.
It's incredible how widely applicable these MZ inequalities are.
Right. Now ready for Ulyanov inequalities.
Except me.
All right. So, Ulyanov inequalities, they connect how smooth a function is to how well we can approximate it using trigonometric polynomials.
So, like, they tell us how well we can build a function using simpler pieces based on how smooth the original function is.
Exactly. And theorem 7.8, that gives us a Ulyanov-type inequality for functions in a Banach lattice. This is the error in our best approximation, but measured in a stronger space, it can be bounded by the error in a weaker space.
Okay, this feels kind of like those Nikolskii inequalities, but now it's about the errors in our approximations, not just the norms themselves.
You're getting it. The ideas are definitely connected. And theorem 7.9, that gives us a similar inequality, but this time for moduli of smoothness, showing us, again, this link between smoothness and how well we can approximate a function.
So basically, Ulyanov inequalities let us put numbers to this idea that smoother functions are easier to approximate.
That's the gist. And that has huge implications for fields like numerical analysis and signal processing, because in those fields, approximating complex functions with simpler ones, that's a core task.
This is also insightful. I'm starting to see how these abstract mathematical ideas actually have real-world uses.
And we haven't even gotten to embeddings of B-soft spaces.
B-soft spaces vaguely rings a bell.
So B-soft spaces, they're a family of function spaces, but they're defined by how smooth the functions in them are. Really useful for looking at functions that have, different levels of regularity.
So we can group functions together based on how smooth they are. But how does this tie back to MZ inequalities?
Well, Corollary 7.1, it lays out these embedding theorems for B-soft spaces, specifically ones with generalized smoothness. And these theorems, they tell us when one B-soft space is actually contained inside another one.
So it's about relationships between spaces based on how smooth the functions in them are.
Exactly. And MZ inequalities are crucial for figuring out these relationships. They give us this powerful way to understand how B-soft spaces are structured and what properties they have.
Wow, this has been an incredible journey. We've gone from the basic theory of these MZ inequalities all the way to seeing how they're used in sampling, approximation, and even the study of all these different function spaces.
A real deep dive, for sure. And we've only scratched the surface, really. There's still so much more to explore.
I've got a whole new appreciation for these inequalities now, like a secret weapon for solving all kinds of problems in analysis.
They really showcase the beauty of math, don't they? How even the most abstract ideas can have these huge implications in so many different fields.
Definitely going to be thinking about this stuff long after we're done here. It's opened up a whole new world for me.
That's what math is all about, right? This constant journey of discovery.
Well said. And to all our listeners out there, we hope this has piqued your interest. We encourage you to keep exploring, keep asking questions. There's always more to learn in the amazing world of mathematics. All right, let's unpack this paper on Marcinkiewicz-Zygmund inequalities.
Okay.
You sent over Marcinkiewicz-Zygmund inequalities in quasi-Banach function spaces.
Yeah.
And it is packed with some serious math.
Oh,
I'm excited to dive in.
it is a fascinating paper for sure.
Yeah.
What struck me was how the authors managed to generalize these inequalities to such a broad range of function spaces.
Yeah.
We're not just talking about your typical LP spaces here.
Right.
They venture into orless spaces,
Oh, yeah.
B-soft spaces, even quasi-Banach spaces.
Yeah, the scope is pretty impressive.
Yeah.
But maybe before we get lost in the weeds,
Yeah.
maybe we should take a step back and remind ourselves what Marcinkiewicz-Zygmund inequalities are all about in the first place.
Absolutely.
Yeah.
At their core, these inequalities provide a way to relate the norm of a function to the values it takes at a specific set of points.
Right.
It's like saying, if you know how the function behaves at these carefully chosen points, you can get a pretty good handle on its overall size.
Right, it's like a mathematical shortcut.
Mm-hmm.
And the classic example, which the paper starts with, in equation 1.1,
Yeah,
is for trigonometric polynomials in LBT.
exactly. Equation 1.1 shows how you can estimate the LP norm of a trigonometric polynomial
Okay.
using just a finite sum based on its values at equally spaced points.
Okay.
It's a beautiful result, and it has implications for all sorts of things like sampling theory and numerical integration.
Okay. So that's the classic setting.
Right,
But this paper takes things much further right.
precisely.
They want to generalize these inequalities to much broader classes of functions and spaces.
And one of their key insights
Okay.
is the importance of Bernstein inequalities.
Okay.
They show that the existence of a Bernstein inequality within a space is a crucial condition for deriving Marcinkiewicz-Zygmund inequalities.
Okay. So what exactly is a Bernstein inequality and why is it so important in this context?
A Bernstein inequality essentially limits how wildly the derivative of a function can behave.
Okay.
It provides a bound on the norm of the derivative. In terms of the norm of the function itself.
So it's like saying the derivative can't be too much bigger than the function itself.
Exactly.
Okay.
And this control over the derivative is essential for the Marcinkiewicz-Zygmund inequality because it allows you to connect the function's values at specific points to its overall behavior.
Okay, that makes sense.
Yeah.
The Bernstein inequality tames the derivative, which then allows you to make those connections between local values and the global norm.
Precisely.
Okay.
And the paper explores this connection in detail, showing how different types of Bernstein inequalities lead to different types of Marcinkiewicz-Zygmund inequalities.
So it's like a framework where the Bernstein inequality is the foundation.
Uh-huh.
And the specific form of the inequality dictates the structure of the resulting Marcinkiewicz-Zygmund inequality.
Exactly.
And the paper is full of examples that illustrate this principle.
That's exciting.
Yeah,
It sounds like they've developed a powerful toolkit for deriving these inequalities.
they have indeed.
Oh.
And another tool they use extensively.
Is the concept of maximal and minimal functions.
Okay, I remember those from my analysis classes.
Yeah.
They're a way to capture the local behavior of a function.
Exactly.
Yeah.
The maximal function tells you the largest value the function takes within a certain neighborhood of a point,
Okay.
while the minimal function tells you the smallest value.
So they're like local scouts reporting back on the extreme values in their assigned territories.
I like that analogy.
Yeah.
And the paper shows how the boundedness of these maximal and minimal functions
Okay.
is another key condition for deriving Marcinkiewicz-Zygmund inequalities.
Interesting.
Yeah.
So it's not just about controlling the derivative.
Right.
It's also about understanding how the function behaves locally.
Precisely.
Got it.
And the authors cleverly weave together these ideas,
Okay.
Bernstein inequalities,
Yeah.
maximal functions, and minimal functions to create a comprehensive framework for deriving and analyzing these inequalities in a wide range of settings.
Okay. I'm starting to see the bigger picture here, but I'm still curious about the specifics.
Okay.
Can you give me an example of how they actually use these ideas to prove a generalized Marcinkiewicz-Zygmund inequality?
Absolutely.
Okay.
Let's take a look at theorem 2.1,
Okay.
which is one of their key results.
Okay.
It establishes a Marcinkiewicz-Zygmund inequality for functions in a Banach lattice
Okay.
that satisfy a certain type of Bernstein inequality.
Okay. Sounds good. Banach lattices and Bernstein inequalities. Here we come.
The proof is actually quite elegant.
Okay.
It starts by using a clever trick
Okay.
involving the generalized Newton-Leibniz formula.
Yeah.
They express the difference between the function at two nearby points
Yeah.
in terms of an integral involving its derivative.
So they're connecting the local behavior of the function.
Yes.
The difference between its values at 2 points
Right.
to its derivative,
Yeah.
which is controlled by the Bernstein inequality.
Exactly. And then they apply the triangle inequality and a change of variables to relate the norm of this difference to the norm of the derivative and the distance between the 2 points.
Okay, so they're using the properties of the Banach lattice
Yeah.
and the structure of the integral to manipulate the expression and bring in the Bernstein inequality?
Precisely.
Okay.
And once they have the Bernstein inequality in play, they can use it to bound the norm of the derivative,
Right.
which ultimately leads to a bound on the norm of the difference between the function's values at the 2 points.
So the chain reaction.
Uh-huh.
They start with a local difference
Yeah.
connected to the derivative.
Right.
Use the Bernstein inequality to control the derivative and end up with a bound that relates the local behavior to the global norm.
Exactly.
Okay.
And this bound is precisely the Marcinkiewicz-Zygmund inequality they're aiming for.
Right.
It relates the norm of the function in the Banach lattice
Okay.
to the maximum and minimum values it attains within a small neighborhood.
Wow, that's pretty slick.
Yeah.
They managed to extract so much information from just a few key properties.
Mm-hmm.
The structure of the Banach lattice,
Right.
the generalized Newton-Leibniz formula, and the Bernstein inequality.
It's a beautiful example of how they leverage the interplay between different mathematical concepts to derive powerful results.
Yeah.
And what's even more impressive is that they don't stop there.
Right.
They extend this result to even more general settings in theorem 2.6,
Okay.
where they work with quasi-Banach spaces and allow for weighted Bernstein inequalities.
Hold on, quasi-Banach spaces?
Yeah.
Didn't we say those were a bit more exotic?
They are, but the core ideas remain similar.
Okay.
They still exploit the relationship between the function's values, its derivatives, and the properties of the space it lives in.
Okay.
The main difference is that they use a Taylor series expansion instead of the generalized Newton-Leibniz formula,
Okay.
and they introduce a weight function to refine their control over the derivatives.
Okay. I'm starting to see the pattern here. They build up their arguments step by step, always relying on the fundamental relationships between a function, its derivatives, and the properties of the space it inhabits.
Exactly.
Okay.
And this meticulous approach is what allows them to push the boundaries of Marcinkiewicz-Zygmund inequalities and unlock their potential for such a wide range of applications.
Okay.
Shall we dive into Theorem 2.6 and unpack how they adapt their strategy for quasi-Banach spaces and weighted Bernstein inequalities?
Let's do it. I'm ready to explore the intricacies of this generalized framework.
All right, so in Theorem 2.6,
Okay.
we're dealing with quasi-Banach lattices.
Yeah.
These are a bit more relaxed than Banach lattices because they don't necessarily satisfy the triangle inequality
Right.
in its usual form.
Yeah.
Instead, they satisfy a modified version,
Yeah.
where the exponent is less than 1.
Okay. I vaguely remember that from my functional analysis days.
Yeah.
Sounds like it could complicate things quite a bit.
It does add some wrinkles,
Yeah.
but the core idea of relating a function's norm to its local behavior remains the same.
Oh.
To handle the quasi-norm,
Okay.
they raise both sides of their inequalities to the power of q,
Okay.
which is the exponent in the modified triangle inequality.
I see. So they're essentially transforming the quasi-norm into something that behaves more like a traditional norm.
Precisely.
Okay.
And this allows them to apply similar reasoning as in Theorem 2.1, but with some adjustments.
Okay.
Instead of the generalized Newton-Leibniz formula,
Right.
they use a Taylor series expansion to represent the function.
Okay.
This makes sense because they assume the function has infinitely many derivatives, a common requirement when working with quasi-Banach spaces.
Okay, so they need a representation that reflects the smoothness properties of the function in this new setting.
Exactly.
Okay.
And here's where the weighted Bernstein inequality comes in.
Okay.
Instead of simply bounding the derivatives,
Right.
they introduce a weight function that modulates the growth of the derivatives.
Why the weight function?
Yeah.
What's the purpose of that?
It's crucial for handling situations where the function doesn't behave uniformly across its domain.
Okay.
Think of a function that oscillates wildly near the endpoints of an interval,
Okay.
but is relatively smooth in the middle.
Okay.
A weighted Bernstein inequality can capture this non-uniform behavior,
Oh,
providing tighter bounds on the derivatives in regions where the function is well-behaved.
that's clever.
Mm.
It's like giving more weight to the regions where the function is smooth and less weight to the regions where it's more erratic.
Precisely.
Okay.
And this nuanced control over the derivatives is key to deriving sharp Marcinkiewicz-Zygmund inequalities
Okay.
in these more general settings.
Yeah.
By carefully choosing the weight function and applying the weighted Bernstein inequality, they can still connect the function's norm to its local values even when the function isn't uniformly smooth.
I'm really impressed with how they've adapted their approach to handle these more complex
Yeah.
scenarios. It seems like they've created a truly powerful framework for understanding and applying Marcinkiewicz-Zygmund's inequalities in a wide range of mathematical contexts.
I agree. Their work has opened up exciting new possibilities for applying these inequalities in areas like approximation theory,
Right.
numerical analysis, and even signal processing.
Yeah.
It's a beautiful example of how abstract mathematical concepts can have tangible impacts on the way we understand and interact with the world around us.
Okay, so we've seen how they handle quasi-norms
Right.
and introduce these weighted Bernstein inequalities.
Yeah.
But I'm still a bit hazy on how it all comes together in the proof of Theorem 2.6.
Sure.
Can we unpack that a bit more?
Of course. Remember, the main goal is still to relate a function's norm to its local behavior.
Right.
Even in these more relaxed spaces. The proof starts similarly to Theorem 2.1.
Okay.
We want to bound the difference between the function's values at two nearby points.
Right, that was the starting point before kind of zooming in on the local differences.
Exactly. But instead of the generalized Newton-Leibniz formula, they
Right.
use a Taylor series expansion this time.
Yeah.
Since we're assuming the function has infinitely many derivatives in this theorem,
Right.
a Taylor series is the natural tool to use.
Makes sense. We need a representation that reflects all that smoothness.
Exactly.
Right.
Now, things get interesting when we apply the triangle inequality
Yeah.
because we're in a quasi-Banach space.
Right.
We need to raise both sides of the inequality to the power of q
Okay.
to handle that modified triangle inequality we talked about.
Ah, clever.
Oh.
It's like tweaking the inequality to fit the quirks of the quasi-norm.
Precisely. Now, each term in our Taylor series expansion has this quasi-norm applied to it.
Okay.
And this is where the weighted Bernstein inequality comes in.
Right.
We use it to carefully bound each of those derivative terms.
So the weight function is doing the heavy lifting here, making sure those derivatives don't blow up and ruin our bounds.
Exactly. The weight function is chosen carefully,
Okay.
depending on the specific space and problem we're dealing with.
Right.
It allows us to account for any non-uniform smoothness the function might have.
It's like custom tailoring the bounds to fit the function perfectly.
Precisely. By controlling the growth of these weighted derivatives,
Okay.
we can finally sum up all the terms in our Taylor series
Yeah.
and get an overall bound.
So even though we're in this more abstract setting with a quasi-norm and potentially wilder functions, we're still able to connect the function's norm to its local behavior thanks to this carefully crafted chain of inequalities.
Exactly. That connection is the heart of their generalization.
Right.
And this bound leads us to the inequality stated in theorem 2.6.
Okay.
They essentially say, if you know the maximum and minimum values the function takes within a small neighborhood, defined by the weight function, you can get a handle on its norm in this quasi-Banach lattice.
Okay, I think I'm starting to wrap my head around the mechanics of this generalized framework.
Good.
Now, I'm curious about those quadrature formulas you mentioned earlier.
Yes.
Where do they fit into all of this?
Quadrature formulas are all about numerical integration.
Okay.
And in the context of Marcinkiewicz-Zygmund inequalities, they provide a systematic way to choose the optimal points for sampling a function.
So they're like a blueprint for efficient sampling.
Yeah, think of it this way. You want to capture the essence of a function with as few points as possible, right?
Right.
Quadrature formulas help you find those most informative points that minimize the error in your representation.
Ah, so it's about squeezing out the most information with the fewest samples.
Exactly. And the paper really dives into this in section 3,
Okay.
particularly in theorem 3.1. They show how you can use quadrature formulas to derive Marcinkiewicz-Zygmund inequalities
Okay.
that use the smallest possible number of sampling points.
I bet this is where those conditions about orthonormal systems and Fourier partial sums come into play.
You're sharp as always.
Right.
They assume you have an orthonormal system in the space.
Right.
And that the Fourier partial sum operator is bounded.
Right.
These conditions, along with the existence of a suitable quadrature formula, are essential for their approach to work.
Sounds pretty technical.
Yeah,
Can we walk through how they actually use this to get those minimal sampling points?
absolutely. The proof of theorem 3.1 is quite elegant.
Okay.
It leverages the idea of duality between a Banach space and its dual space.
Okay. I remember duality from my functional analysis days.
Mm-hmm.
It's about pairing elements from a space with elements from its dual space.
Yes, it's like a mathematical dance between two spaces.
Okay.
Each element in one space has a partner in the other,
Right.
and their interaction tells you something about the structure of both spaces.
Got it. So how does this mathematical dance help us with the MZ inequalities?
They show that if you can bound the norm of a certain object in the dual space,
Okay.
you automatically get a bound on the norm of the polynomial in the original space.
Interesting. It's like proving something indirectly by working in the mirror image of the original space.
Exactly. And to prove this bound in the dual space,
Okay.
they cleverly use the quadrature formula.
Right.
It allows them to express the norm in the dual space as a sum over the sampling points.
Okay.
Which is precisely what we need for a Marcinkiewicz-Zygmund inequality.
So duality helps us shift the problem to a different space.
Huh?
And then the quadrature formula swoops in to give us the expression we need. That's pretty neat.
It is, but we need a couple of things to make sure this all works.
Okay.
First, we need that trusty Bernstein inequality.
Yeah.
To control the growth of the derivatives, just like in the previous theorems.
Right. The Bernstein inequality is like our loyal sidekick at this point, always there to keep those derivatives in check.
Exactly. And second, we need those sets
Right.
that cover the domain of the function to be well-behaved.
Okay.
They need to be distributed in a way that ensures our sampling points capture the function's behavior effectively.
So it's a delicate balance.
Yeah.
Control the derivatives with the Bernstein inequality and make sure our sampling points are strategically placed, thanks to those well-behaved sets.
You got it. By combining these ingredients, duality, quadrature formulas, the Bernstein inequality, and a nicely distributed covering of the domain, they can derive Marcinkiewicz-Zygmund inequalities with a minimal number of sampling points.
It's like finding the most efficient way to compress information about a function without losing its essence.
Precisely. And this efficiency is particularly valuable in applications where computational resources are limited.
Okay, we've covered the general framework for deriving MZ inequalities in various spaces,
Right.
from familiar LP spaces to those more exotic quasi-Banach lattices.
Right.
And we've seen how quadrature formulas help us pick the best sampling points.
Yes.
I'm ready to see these general principles in action.
Okay.
Can we look at some specific examples?
Absolutely. Let's start with trigonometric polynomials,
Okay.
a classic case where MZ inequalities have been studied extensively.
Right.
Section 4 of the paper dives into this, starting with the minimal set of nodes needed to capture the norm of a trigonometric polynomial in a Banach lattice.
I remember seeing equation 4.2.
Yeah.
It looks similar to the classic MZ inequality for LP spaces.
Yes. Equation 4.2 captures that core idea of relating the norm to a sum over the function's values at equally spaced points. But what's impressive is that they prove this for any translation invariant Banach lattice on the torus. It's a much broader class of spaces.
So they're taking a classic result and showing it holds in a much wider setting.
Exactly. And the proof of theorem 4.1, which establishes this generalized result, is surprisingly straightforward.
Okay.
It relies on theorem 3.1, which we just discussed, and the classic Bernstein inequality for trigonometric polynomials.
They're building on their previous work to establish new results. It's like a mathematical chain reaction.
Precisely. They show that trigonometric polynomials in a translation invariant Banach lattice satisfy the conditions of theorem 3.1.
Okay.
And that immediately gives us the MZ inequality with a minimal set of nodes.
That's elegant. I'm really starting to appreciate the power and flexibility of their framework.
And this is just the beginning. They go on to explore MZ inequalities for trigonometric polynomials in even more general settings like quasi-Banach lattices and Orless spaces.
I remember seeing some results about Orless spaces in section 4.4.
Yes.
What's so special about Orless spaces?
Orless spaces are a generalization of LP spaces.
Okay.
They give you more flexibility in defining the norm.
Okay.
Using something called an Orless function.
Okay.
This allows you to tailor the space to fit the specific growth properties of the functions you're working with.
So it's like customizing the space instead of forcing the functions to conform to a predefined mold.
Exactly. And this customization is super useful when dealing with functions that behave differently than what traditional LP norms can capture.
Okay, that makes sense. What kind of MZ inequalities do they get for these custom-fit Orless spaces?
They present a couple of interesting results. One focuses on the Orless norm itself.
Okay.
The other explores what happens when you allow for non-uniform sampling points.
Non-uniform sampling.
Yeah.
Doesn't that make things a lot more complicated?
It does add some challenges, but they handle it beautifully.
Okay.
For example, theorem 4.13 establishes MZ inequalities where the spacing between sampling points can vary.
Okay.
As long as the minimum and maximum distances between those points meet certain criteria.
So they're relaxing that strict requirement of equally spaced points while still getting meaningful results. That's impressive.
It is. And they achieve this by cleverly using the properties of the Orlich function and carefully bounding the terms in the MZ inequality.
Okay.
Their results highlight the power of Orlich spaces for handling functions with non-uniform behavior and demonstrate how adaptable their general framework is.
This is fascinating.
Yeah.
They're pushing the boundaries of MZ inequalities in every direction, exploring different spaces, different sampling schemes, and different function classes.
They are. And they do all of this with a remarkable level of rigor and clarity in their arguments.
Yeah.
Their work truly showcases the power of abstract math to uncover the intricacies of approximation and provide tools for real-world problems.
Okay, I'm ready for more examples.
All right.
What other function classes do they delve into?
Next up are algebraic polynomials.
Okay.
Those workhorses of approximation theory.
Right.
Section 5 focuses on this case.
Okay.
But things get a bit trickier here.
Trickier. I thought algebraic polynomials were relatively well behaved compared to some of the other functions we've discussed.
True. But the challenge on a bounded interval is that they can grow very rapidly near the endpoints.
Okay.
This means the classic Bernstein inequality, which has been our go-to tool, might not be enough to control the growth of their derivatives.
Ah, I see. The Bernstein inequality's uniform bound might not capture those nuances at the edges.
Precisely. So to address this, they introduce a weighted version of the Bernstein inequality.
Okay.
The weight function is carefully designed to tame the growth of those derivatives near the endpoints.
So it's like giving more weight to those potentially problematic regions where the derivatives could explode.
Exactly. And this weighted Bernstein inequality is key to deriving sharp MZ inequalities for algebraic polynomials on bounded intervals.
I'm guessing this is where that function Lx from section 5 comes in.
Spot on. That's the weight function they use in their weighted Bernstein inequality.
Okay.
It's carefully chosen to effectively control the growth of the derivatives near the endpoints while still behaving well in the interior of the interval.
It sounds like a delicate balancing act.
Yeah.
Too strong, and it overpowers the function elsewhere. Too weak, and it doesn't control the edges.
You got it. It's all about finding that sweet spot. In Proposition 5.3, for example, they present a weighted Bernstein inequality for algebraic polynomials on the interval matus 1, 1.
Okay.
Using the weight function 1 by 2 plus 1n,
Okay.
this weight function goes to 0 at the endpoints,
Okay.
effectively suppressing the growth of those derivatives there while remaining well-behaved in the interior.
Okay. I'm starting to see how this weighted approach helps them adapt their framework to the specific challenges posed by algebraic polynomials.
Indeed. And they demonstrate the effectiveness of this approach by deriving a series of MZ inequalities for algebraic polynomials, both in Banach lattices and in quasi-Banach lattices.
I remember seeing some results about minimal sets of nodes for algebraic polynomials. How does that work in this context?
That's covered in section 5.3, where they delve into the case of orthogonal polynomials.
Okay.
Orthogonal polynomials have this amazing property where their zeros are always real distinct and lie within the interval where the weight function is positive.
So those zeros are like perfectly placed sampling points.
Exactly. They provide a natural set of sampling points that are well distributed within the interval.
Okay.
And in theorem 5.5, they prove that under certain conditions,
Right.
you can derive MZ inequalities for algebraic polynomials using precisely those zeros as the sampling points.
That's incredible. They're exploiting the inherent structure of orthogonal polynomials to choose the optimal sampling points.
Precisely. And this connection between orthogonal polynomials and MZ inequalities has deep implications for fields like numerical integration.
Approximation theory?
I'm truly starting to appreciate the beauty and power of their approach.
Yeah.
They're not just deriving abstract results.
Right.
They're uncovering deep connections between different areas of math and using those connections to develop powerful tools.
I agree. Their work is a beautiful blend of abstract theory and practical application.
Okay, I'm ready for even more examples.
Aye.
What other function classes do they tackle?
In section 6, they broaden their scope even further,
Okay.
exploring a variety of other function classes,
Okay.
including band-limited functions, splines,
Yeah.
exponential sums, and Mudob's polynomials.
Wow, that's quite a lineup. Let's start with band-limited functions. What are those, and how do they fit into the MZ inequality framework?
Band-limited functions are those whose Fourier transforms have compact support.
Okay.
Their frequency content is restricted to a certain range.
Okay.
They're like signals that have been smoothed out to remove high-frequency noise.
So they're all about that low-frequency life. Exactly. And they have some nice properties that make them amenable to MZ inequalities.
Okay.
In particular, they satisfy a version of the Bernstein inequality that relates the norm of their derivatives to their bandwidth.
Ah, so they're still playing by the rules of the MZ inequality game,
Yeah,
even though they live in the world of frequencies.
precisely. And in section 6.1,
Right.
the paper explores MZ inequalities for band-limited functions in both Banach lattices and quasi-Banach lattices,
Okay.
deriving results that are analogous to those for trigonometric and algebraic polynomials.
So it's like they're showing that their framework is versatile enough to handle functions from different domains, whether it's time or frequency.
Exactly.
Hmm.
And this adaptability is one of the strengths of their approach.
Okay, what about splines? I remember those from my computer graphics days. They're piecewise polynomial functions used for smooth curve fitting, right?
That's right. Splines are widely used in computer graphics, numerical analysis,
Yeah.
and many other fields where you need to represent smooth curves or surfaces.
But I thought we were dealing with functions defined on the torus, not curves or surfaces. How do splines fit into this picture?
You're right that splines are often used to represent curves or surfaces,
Right.
but you can also think of them as functions defined on an interval.
Okay.
And in section 6.2, the paper focuses on periodic splines, which are splines defined on a closed interval that satisfy certain periodicity conditions.
Ah, so they're splines that wrap around like a snake biting its own tail.
Exactly. And these periodic splines can be treated as functions on the torus,
Right.
which brings them into the realm of MZ inequalities.
Okay, that makes sense.
Hmm.
So what kind of MZ inequalities do they derive for splines?
They present a result in theorem 6.6
Okay.
that relates the norm of a periodic spline in a translation invariant Banach lattice to a sum over its values at equally spaced points.
So it's a similar flavor to the MZ inequalities for trigonometric polynomials.
Exactly. And the proof relies on a Bernstein-type inequality for splines,
Okay.
which bounds the norm of their derivatives in terms of the spacing between the knots.
Okay. I'm starting to see a pattern here. It seems like for every function class, they consider they need a suitable Bernstein-type inequality to control the growth of the derivatives.
You're absolutely right. The Bernstein inequality in its various forms
Right.
is a cornerstone of their approach.
Yeah.
It's the key to connecting the local behavior of a function to its overall norm, which is the essence of MZ inequalities.
This is fascinating.
Yeah.
It's like they're building a universal toolkit for deriving MZ inequalities. And the Bernstein inequality is the master key that unlocks the door to a wide variety of function classes.
I like that analogy. They're providing a powerful framework for understanding and applying MZ inequalities in a truly comprehensive way.
Okay, we still have two more function classes on our list.
Yeah.
Exponential sums and Minet's polynomials. What
Yeah.
can you tell me about those?
Both exponential sums and Minet's polynomials
Okay.
involve linear combinations of functions with specific growth properties.
Okay.
Exponential sums are linear combinations of exponential functions with different exponents, while Minet's polynomials are linear combinations of power functions with exponents that can be real numbers.
Okay, so they're both about combining functions that grow at different rates.
Precisely. And this makes them particularly interesting from the perspective of MZ inequalities,
Okay.
because the growth of the functions can significantly impact the behavior of the derivatives and the choice of optimal sampling points.
So it's like they're adding another layer of complexity to the MZ inequality puzzle.
Exactly. And in sections 6.3 and 6.4, the paper delves into these complexities, deriving MZ inequalities for exponential sums and Minet's polynomials in various settings.
Can you give me a taste of what these results look like?
For exponential sums,
Okay.
they focus on the case of rearrangement invariant Banach spaces, which are spaces where the norm of a function depends only on the distribution of its values,
Right.
not their specific order.
Okay, so it's like the space doesn't care about the arrangement of the function's values, just how they're spread out.
Exactly. And in theorem 6.8,
Okay.
they prove that under certain conditions,
Okay.
you can derive MZ inequalities for exponential sums in these spaces using equally spaced points.
So even though the functions themselves involve exponents, the sampling scheme can still be quite simple.
Indeed. And the proof relies on a Bernstein-type inequality for exponential sums,
Okay.
which bounds the norm of their derivatives in terms of a quantity that reflects the growth of the exponents.
Okay, I'm starting to see a familiar pattern here. They adapt their framework to each function class by finding a suitable Bernstein-type inequality.
You're catching on. And for Minet's polynomials,
Okay.
they focus on rearrangement invariant Banach spaces that satisfy an additional condition related to the substitution xs.
Okay.
This condition essentially allows them to transform the Minet's polynomials into exponential sums,
Okay.
which they can then handle using their previous results.
Ah, so they're cleverly using a transformation to leverage their existing toolkit.
Exactly. And in theorem 6.9, they present an MZ inequality for Minet's polynomials in these spaces, again using equally spaced points.
It's impressive how they're able to extend their framework to handle such a diverse range of function classes, from the classic trigonometric polynomials to the more exotic Minet's polynomials.
Indeed. Their work provides a comprehensive and insightful overview of MZ inequalities, demonstrating their power and versatility in a wide range of mathematical settings.
Okay, I'm really impressed with their thoroughness and the elegance of their approach. But before we get completely lost in the world of theoretical results, let's step back and talk about applications. How do these MZ inequalities actually connect to real-world problems?
That's a great question. And the paper doesn't shy away from exploring the practical implications of their theoretical work. In section 7, they delve into a variety of applications ranging from approximation theory to embedding theorems for B-sub spaces.
Okay, I'm intrigued. Let's start with approximation theory. How do MZ inequalities play a role in that field?
Well, approximation theory is all about finding the best way to approximate a given function using simpler functions like polynomials or trigonometric polynomials.
Right. I remember that from my numerical analysis classes. We used to spend hours trying to find the best polynomial fit for a set of data points.
Exactly. And MZ inequalities can be incredibly useful in this context because they provide a way to bound the error of an approximation in terms of the function's values at specific points.
So they give you a measure of how good your approximation is.
Precisely. And in section 7.1,
Okay.
they demonstrate this connection by exploring the approximation of functions using sampling operators.
I remember seeing something about sampling operators earlier in the paper. They're like mathematical machines that take a function as input and spit out an approximation based on the function's values at specific points, right?
Exactly. And they're crucial in areas like signal processing,
Right.
where you often need to reconstruct a continuous signal from a set of discrete samples.
Okay, that makes sense. So how do MZ inequalities help analyze these sampling operators?
Well, in theorem 7.1,
Okay.
they prove that the error of a specific sampling operator, the Lagrange interpolation operator, can be bounded in terms of the error of the best one-sided approximation of the function by trigonometric polynomials.
Okay, that sounds pretty technical. Can you unpack it a bit?
Essentially, they're saying that if you know how well you can approximate the function using trigonometric polynomials,
Okay.
you can automatically get a bound on how well a specific sampling operator will perform.
So it's like a shortcut for analyzing the accuracy of the sampling operator.
Exactly. And this shortcut is made possible by the MZ inequality for trigonometric polynomials.
That's clever.
Yeah.
They're using the MZ inequality to connect two seemingly different concepts.
Mm-hmm.
The error of a sampling operator and the error of a trigonometric polynomial approximation.
Precisely. And this connection is a testament to the far-reaching implications of MZ inequalities in approximation theory and related fields.
Okay, I'm convinced that MZ inequalities are a powerful tool for analyzing approximation schemes. What other applications do they highlight?
Another interesting application they explore is Nikolskii inequalities. Nikolskii inequalities are a fundamental tool in approximation theory.
Right.
And many other areas of mathematics. They relate the norms of a function in different spaces, typically involving different powers of the function.
Okay. I vaguely remember seeing Nikolsky inequalities in my functional analysis classes. They're about comparing how big a function is in different spaces.
Right, exactly. And in section 7.2,
Okay.
they demonstrate how MZ inequalities can be used to derive Nikolsky inequalities for trigonometric polynomials in a variety of settings, including translation invariant Banach lattices and Orlet spaces.
So they're using MZ inequalities to establish connections between different norms.
Precisely. And these connections are essential for understanding the behavior of functions in different spaces and for developing sophisticated approximation techniques.
I'm really starting to see the breadth and depth of their work. They're not just focusing on one specific type of inequality or one specific function class. They're exploring a whole web of interconnected concepts and applications.
I agree. Their approach is remarkably comprehensive and insightful.
Okay, what about those B-solve spaces you mentioned earlier? How do they fit into this picture?
B-solve spaces are a family of function spaces that play a crucial role in modern analysis.
Okay.
They're defined using a combination of smoothness properties and integrability properties.
Okay, so they're like a hybrid of smoothness and integrability.
Exactly. And they're widely used in areas like partial differential equations,
Right.
image processing, and signal analysis.
So they're pretty important spaces.
Yeah.
How do MZ inequalities connect to them?
Well, in section 7.4,
Okay.
the paper explores embedding theorems for B-solve spaces.
Okay.
Embedding theorems are statements that tell you when one function space is contained within another function space.
Okay, so it's like a hierarchy of spaces.
Precisely. And they show that MZ inequalities can be used to derive embedding theorems for B-solve spaces with generalized smoothness,
Okay.
which are a generalization of the classic B-solve spaces.
So they're pushing the boundaries of B-solve spaces and using MZ inequalities to navigate this new territory.
Exactly. Their work highlights the deep connections between MZ inequalities, Nikolsky inequalities, and embedding theorems for B-solve spaces, revealing a rich tapestry of mathematical concepts that are woven together to form a powerful tool for analyzing functions and their approximations.
This is all incredibly impressive. I'm starting to feel like I've only scratched the surface of this paper. There's so much depth and so many fascinating connections.
I agree. This paper is a true gem. It's a testament to the power of abstract mathematical concepts to illuminate the intricacies of approximation theory and to provide a framework for solving real-world problems in areas like signal processing, image analysis, and numerical computation.
Well, I think we've covered a lot of ground today, exploring the general framework for deriving MZ inequalities, delving into specific examples for various function classes, and even touching on some of the fascinating applications of these inequalities in areas like approximation theory, Nikolskii inequalities, and embedding theorems for B-soft spaces.
Indeed, we've taken quite a journey through the world of MZ inequalities.
I'm feeling a bit overwhelmed, to be honest, but in a good way. It's inspiring to see how much depth and beauty there is in this seemingly niche area of mathematics.
I share that sentiment. The elegance and power of their approach are truly remarkable.
It really is amazing how these inequalities bridge pure math with these concrete applications. Before we wrap up, though, there was one thing that caught my eye early on in the paper that I wanted to revisit. It's equation 1.2, where they rewrite the classic MZ inequality in terms of the simple interpolating function. What's the significance of that?
Ah, good eye. That equation highlights a subtle but crucial insight. It's not just about picking the right points to sample the function.
Right.
It's about how those points partition the domain.
Okay, I see what you mean. The points define these little subintervals.
Yeah.
And the MZ inequality relates the function's norm to how it behaves within those subintervals.
Precisely. And the choice of those subintervals, or how you partition the domain, can really impact the sharpness of the MZ inequality.
So it's not just about finding the right points. It's about finding the right way to carve up the space.
Exactly. And the paper subtly emphasizes this throughout their discussion of different function classes and spaces. They show that the partitioning scheme should be tailored to the specific properties of the functions and the space you're working with.
It's like a tailor making a custom suit. The cut and fit have to be just right for the wearer.
I love that analogy. They're essentially tailoring the partitioning scheme to fit the function and the space, ensuring the resulting MZ inequality captures the function's behavior with minimal information loss.
That's such an insightful point. It adds a whole new layer of depth to these inequalities.
It does, and it highlights the importance of careful analysis and deep understanding of the mathematical structures when working with MZ inequalities.
Okay, I'm thoroughly convinced that Marcinkiewicz-Zygmund inequalities are a powerful and versatile tool for mathematicians working across a wide range of fields.
Absolutely. They provide a framework for understanding the fundamental relationships between a function, its derivatives, the space it lives in, and the points at which it's sampled.
And they have applications in areas like signal processing, numerical integration, and approximation theory, to name just a few.
Indeed. And as this paper so beautifully demonstrates, their potential is still being explored with new generalizations and applications emerging all the time.
This has been a truly deep dive. I feel like we've only just scratched the surface of this paper. There's so much depth and so many fascinating connections.
I agree. It's been a rewarding journey through the world of MZ inequalities.
I'm feeling a bit overwhelmed, to be honest, but in a good way. It's inspiring to see how much depth and beauty there is in this area of mathematics.
I couldn't agree more. The elegance and power of these inequalities are truly remarkable. They showcase the beauty of abstract mathematical concepts and their potential to impact our understanding of the world around us.
Well, on that note, I think it's time to resurface from this deep dive into the fascinating world of Marcinkiewicz-Zygmund inequalities. Until next time. Welcome back, everyone. Ready for another deep dive?
Absolutely. Always excited to see what we're exploring today.
Well, today we're tackling some seriously fascinating higher-level math.
Ooh, sounds intriguing.
It is. We're digging into Marcinkiewicz-Zygmund inequalities. You gave me this really interesting paper all about them.
Ah, yes, that one's packed with some cool insights.
It is. And knowing you and our listeners, I think we can skip the 101 level stuff and head straight for the heart of the matter.
Yeah, let's jump right into the good stuff.
Exactly. So get ready to see how something seemingly simple, like, just picking out specific points on a function, can unlock a whole deeper understanding of how it behaves, especially within, like, all these different mathematical spaces.
I love how this paper really stretches the classic Marcinkiewicz-Zygmund inequality beyond its, usual boundaries.
Yeah, it's not just sticking to trigonometric polynomials and LP spaces anymore.
Right. They're really pushing it to a wider range of spaces, like even those Banach and quasi-Banach lattices.
Okay, yeah, pages 1 and 2 dive right into that. We've got Banach lattices, quasi-Banach lattices, translation invariant spaces, rearrangement invariant spaces, dense stuff.
It is, but each of these spaces brings its own kind of personality, its own set of rules.
Right, like a fingerprint.
Exactly. Like Take Banach lattices. You can measure the size of a function and its absolute value there. Quasi-Banach lattices loosen up the rules a bit.
Some more flexibility.
Exactly. And then you've got those spaces where, like, if you shift the function or rearrange its values, its size doesn't actually change. That's translation and rearrangement invariance.
Okay, so understanding these different spaces is key to how those Marcinkiewicz-Zygmund inequalities actually work, right?
Exactly. It's about choosing the right tool for the job, you know?
Gotcha. So let's see how they put these tools to work. Pages 2 to 8 really get into the nitty-gritty boundedness of maximal and minimal functions.
Yeah, that's where those surprising connections start popping up. How a function behaves locally versus, like, its overall size within a space.
I'm seeing a lot of equations here about derivatives, maximums, minimums, all within specific intervals. Can you break it down for us? Like, what's the big picture these maximal and minimal functions are trying to capture?
Okay, so imagine you have a function, right? And picture tiny little cubes around each point in its domain.
Okay, got it.
The maximal function basically tells you the highest peak of the function within each cube. And the minimal function, well, it captures the lowest valley.
So it's like creating this super detailed topographic map of the function.
Exactly. And those peaks and valleys, they can tell us a lot about the function's overall size, especially when you factor in things like the Bernstein inequality.
Theorem 2.1 seems like a big deal here. It connects the boundedness of those maximal and minimal functions to the norm of the function in a translation invariant Banach lattice.
Right. It's basically saying that if a function obeys a Bernstein inequality, which limits how fast its derivatives can change, then we can figure out its norm just by looking at those maximal and minimal functions.
So the wiggliness of the function, how much its derivative jumps around, that actually tells us about its overall size, even in these kind of abstract spaces.
Precisely. It's all about those hidden connections.
I love it. And they actually use the generalized Newton-Leibniz formula to prove this, which is pretty cool.
Yeah, they express the difference between the function's values at 2 points as an integral of its derivative.
Okay.
And then, by using the Bernstein inequality, they show how those local differences contribute to the overall norm of the function.
I'm really liking this geometric interpretation they give too. If a function follows a Bernstein inequality, its graph has to stay within this tube around its average value.
It's like the function is confined, right?
Right.
Like the smoother it is, the narrower the tube gets. And that tells us even more about the relationship between its local wiggles and its overall size.
So cool how they bring in this visual element. And the paper doesn't stop there. There's a bunch of insightful remarks that add even more depth.
Yeah, like remark 2.2 points out that the size of those cubes we were talking about, they can't be just anything.
Oh, right. If they're too big, we might miss important details.
Exactly, especially for functions that change rapidly.
And remark 2.3 hints that we can actually stretch this theorem to even more general Banach lattices, as long as the derivatives still play nice within the space.
Right. Got to make sure we're still following the rules of the game, you know.
For sure. Now, remark 2.4 talks about this connection between the Bernstein inequality and the supremum norm, like a shortcut.
It is. It gives us a way to prove Bernstein inequalities in more complex spaces if we can show the derivative is well-behaved in terms of its supremum norm. We don't have to start from scratch every time.
I appreciate these shortcuts. And then remark 2.5 gives us another visual teat. If a function follows a Bernstein inequality, its norm is basically connected to the average value within those little cubes.
Right, like we're smoothing out the local bumps to get a better sense of the overall size.
Smoothing it out, I like that. This is all setting us up nicely for Theorem 2.6, where things get even more general.
Yeah, we're moving into the realm of quasi-Banach spaces and weighted Bernstein inequalities.
Okay, now we're talking quasi-Banach spaces. Those are even more flexible, right?
They are. And to handle that flexibility, they introduced the weighted Bernstein inequality. That weight function, they call it, Quinn, lets us fine-tune things.
Especially for functions that aren't periodic, right?
Exactly. It's all about making sure our tools are precise enough for the job. But they do need the functions to have lots and lots of derivatives, infinitely many, in fact.
Why is that?
Well, it all comes down to Taylor's formula in the proof. Infinite differentiability means we can get super accurate local approximations using those derivatives.
So we need that smoothness to really make those weighted Bernstein inequalities work their magic.
You got it. But they do acknowledge that this might not always be realistic, especially for things like splines.
Right. Splines don't always have that infinite smoothness. So it's a good reminder that even the most powerful tools have their limitations.
Absolutely. Choosing the right tool is always key.
So true. And remark 2.7 gives some helpful advice on adapting to different situations, right? Like if we know some derivatives are better behaved than others.
Exactly. Or if the Bernstein inequality involves a more complicated function of n, not just a simple power.
It shows how flexible this framework really is. And then there's that example in remark 2.8 with algebraic polynomials on a bounded convex set. What makes those special?
Well, for them, the Bernstein inequality takes on a slightly different form.
How so?
It involves this thing called the Ditzian-Totic modulus, which takes into account the shape of the set where the polynomial is defined.
So the geometry of the set itself matters.
It does. And by incorporating that geometric information into the Bernstein inequality, we get Marcinkiewicz-Zygmund inequalities specifically designed for those polynomials on convex sets.
Wow, the deeper we go, the more connections we find. And this is just the first part of our deep dive. I can't wait to see how those general Marcinkiewicz-Zygmund inequalities for quasi-Banach spaces play out in theorems 2.9 and 2.n.
Me too. The journey is just beginning. Picking up where we left off, theorem 2.9, it brings us back to those translation invariant Banach lattices. You know, those spaces where shifting a function around doesn't actually change its overall size.
Yeah, those are pretty interesting.
So this theorem basically shows that if we can kind of slice up the function's domain into these smaller sets that meet certain geometric conditions, we can actually figure out the function's norm just by looking at its maximum and minimum values within each set.
Okay, I see those conditions in equations 2.0 and 2.11. They're making sure those smaller sets cover the whole domain without being too big.
Exactly. We got to capture the function's behavior everywhere, but also zoom in enough to see those fine details. And the proof, it builds on what we saw in theorem 2.1.
Right. That's where we linked the local behavior, those derivatives, to the overall norm. So now we're taking those local pieces and putting them together.
Exactly. It's like building a giant mosaic. Each local estimate is a tile, and theorem 2.9 gives us the instructions to arrange them all. Oh, and something cool they point out is that the left side of inequality 2.1, you know, the one that gives the lower bound on the norm, that part still works even if we relax some of those geometric rules.
So even if we don't perfectly understand the function's behavior everywhere, we can still get some idea of its overall size just by looking at its peak values.
Precisely. Even incomplete information can be valuable. And they actually give a concrete example in the proof to show this in action. Always nice to see those tangible examples.
Definitely. Okay, so moving on to theorem 2.0, this feels like the grand finale of this section. Those general Marcinkiewicz-Zygmund inequalities for quasi-Banach lattices.
It is. This theorem brings together everything we've been talking about. It says under certain conditions, we can estimate a function's norm in a quasi-Banach lattice by sampling it at specific points. And then we use those samples to build a kind of simplified, piecewise, constant approximation of the function.
Okay, hold on. Lots to unpack there. What are those certain conditions?
So first, we still need that weighted Bernstein inequality to keep those derivatives in check.
Makes sense.
Second, we got to split the function's domain into smaller sets, like we did before. But now, here's the twist. Within each set, we introduce a new bunch of points where we sample the function.
I see them, the y points in equation 2.14. And they got to be close to the x points that define those smaller sets, right?
Right. Got to make sure those y points accurately capture what's going on in each set. So we basically stitch together all these local snapshots to create a rough sketch of the function. And what this theorem shows is the norm of that sketch is closely related to the norm of the real function.
Wow, it's like a cosmic game of connect the dots. But instead of a picture, we're revealing something fundamental about the function.
That's a great way to put it. We're using those cleverly chosen sample points to get a glimpse of the big picture.
It's amazing that we can estimate a function's norm just by focusing on a handful of its values, like we're zooming in to see the underlying structure.
Exactly. And they emphasize in remark 2.11 that the weight function, that little addition we made to the Bernstein inequality, it's crucial for making this whole thing work, especially for those non-periodic functions.
Right. It helps us adjust our measurements to the specific quirks of each function.
Exactly. And they also point out that if we're dealing with periodic functions where the weight function is constant, things simplify quite a bit. We don't need to be as picky about the geometry of those smaller sets.
That makes sense. Periodic functions have that nice repeating pattern. No need for as much fine-tuning.
Right. And so ends section 2. A very thorough journey through the theoretical foundations of these generalized Marcinkiewicz-Zygmund inequalities.
I'm starting to grasp just how powerful these inequalities can be. It's like they're giving us a new language to describe the behavior of functions.
Absolutely. They really highlight the power of abstract thinking in mathematics. By zooming out and focusing on the core properties, we reveal these deep connections.
Connections that go way beyond what we might initially expect. And I have a feeling we're just getting started. The paper dives into specific examples, optimizations, even applications of these inequalities.
Yeah, things are about to get even more interesting.
All right, so we've built up a solid understanding of the theory behind these generalized Marcinkiewicz-Zygmund inequalities, but there's always that question of efficiency, right?
Yeah, can we get the same insights with less work, basically?
Exactly. And that's where the paper goes next, right into minimizing the number of points we need to sample a function.
Right, on page 8, yeah. They call it Marcinkiewicz-Zygmund type inequalities with a minimal number of nodes. Love the name.
Catchy. And they start with quadrature formulas, right?
Those are key here. They're a way to, like, approximate integrals numerically. So instead of having to do this whole complex integral, you pick some clever points, give them weights, and boom, boom. You've got a finite sum that represents the integral.
I see that in equation 3.1. They're defining a quadrature formula specifically for trigonometric polynomials.
Right, and those weights, the lambda j's, they're tied to this special kernel called the de la Vallée-Poisson kernel.
Ah, that rings a bell. It's really good for approximating functions, right?
It is. And that's essential here because we're trying to minimize the points we sample while still getting an accurate estimate.
Gotcha. Then they bring in this idea of generalized translation. I see it in equation 3.2th.
Yeah, think of it as like a souped-up version of regular translation. We can shift functions in a more abstract way now, which gives us more flexibility.
Okay, I'm seeing how all these pieces are fitting together. They're building a framework to figure out the absolute minimum number of points we need to sample a function and still capture its essence.
Exactly. But there are some rules, of course. Theorem 3.1 lays them all out. We need the right kind of quadrature formula, certain conditions on the function's behavior, and specific relationships between those quadrature weights and the kernel we're using.
It's like a delicate balancing act, making sure we're being efficient without sacrificing accuracy.
Definitely. And for me, what really stands out in Theorem 3.1 is their use of those de la Vallée-Poisson type kernels. Remember how we said they're good for approximating functions?
Yeah, those were key.
Well, that's exactly why they're so powerful here. They help us squeeze the most information out of the fewest data points possible.
Love it. So they've set up the theory, and now it's time to put it into practice. And they start with trigonometric and algebraic polynomials.
Yeah, those are like the bread and butter of a lot of math. Always good to see how these abstract ideas play out in familiar territory.
Exactly. And theorem 4.1 on page 13, that's where they establish those Marcinkiewicz-Zygmund inequalities for trigonometric polynomials. Gives us concrete estimates based on those strategically chosen sampling points.
And not only estimates, but also like the conditions under which those estimations hold true. So it's not just a guess, it's a solid result.
Very cool. And they explore different kinds of nodes too, right? Uniform and non-uniform. What's the difference there?
Well, uniform nodes, those are the ideal scenario, like perfectly spaced sampling points. But in the real world, things aren't always so neat. We might have to deal with unevenly spaced points, those non-uniform nodes.
Ah, so it's like being prepared for messy data.
Exactly. And what they show is that even with those messy, non-uniform nodes, we can still get meaningful results.
That's reassuring. It's like knowing that our mathematical tools can handle real-world situations.
Precisely. And then they move on to algebraic polynomials in section 5.
More familiar faces.
Right. And
Wow.
theorem 5.5 gives us a concrete Marcinkiewicz-Zygmund inequality for those.
Another tool for the toolbox. But they don't stop there, right? There are even more function classes, band-limited functions, splines, exponential sums, even Muntz polynomials.
They really want to show how widely applicable these inequalities are. It's like they're uncovering this underlying unity across all these different kinds of functions.
Love that. It's like a universal language for understanding functions.
Yeah.
And speaking of understanding, the paper doesn't just stay theoretical. It actually talks about real-world applications in the last section.
Yeah, section 7 is all about showing how these seemingly abstract ideas can actually be used to solve problems.
Like what kind of problems?
Well, they go into approximation by sampling operators, Nikolskii inequalities, best approximation inequalities, and even Bisov spaces. It's a wide range.
Wow, so we've gone from those basic principles all the way to practical applications. This paper really has it all.
It does. And it beautifully demonstrates the power of connecting those local insights, like the behavior around a single point, to a global understanding of the function.
So well said. And for our listeners, we hope this deep dive has given you a new appreciation for the beauty and usefulness of Marcinkiewicz-Zygmund inequalities. The world of functions is vast and fascinating, and these inequalities provide a powerful way to explore it. Until next time, keep diving deep into those mathematical wonders. Welcome back to the deep dive. Today, we're going deep into this paper by Kolomoitsev and Tikhonov, Marcinkiewicz-Zygmund inequalities in quasi-Banach function spaces.
Oh, a great choice.
Yeah, it's a fascinating topic, and we all know as math experts how important inequalities are.
Right, yeah.
But what's so special about Marcinkiewicz-Zygmund's inequalities, or MZ inequalities, as I'll probably call them for short?
Well, they give us this really cool link between the continuous and the discrete. They're all about, like, connecting the norm of a function to the norm of, like, a very specific simple function that samples it.
So kind of like almost, I don't know, you think about like a curve and then just picking a few points along it.
Exactly. Capturing the essence with just a few well-placed points.
Okay, I like that. And this paper specifically is taking us beyond the familiar LP spaces into Banach and quasi-Banach functions spaces. And they use Bernstein inequalities to derive these MZ inequalities.
Yeah.
And that's applicable to, we've got polynomials, splines, even entire functions of exponential type.
It's really quite remarkable how versatile it is. And it all begins really on page 1 with this, sort of classic MZ inequality for trigonometric polynomials in LPT.
Okay.
Equation 1.1 shows this really beautifully. It shows how the LP norm of this polynomial is like squeezed between these two expressions that involve the sums of the values at equally spaced points. And this squeezing, this bounding is very important in things like discretization theory, because it tells us how accurately we can represent a continuous function using just these, discrete samples.
Yeah.
And equation 1.2 gives us another kind of perspective on this. It relates the norm to the norm of a simple function that sort of interpolates it at these specific points.
So we're highlighting the idea of taking the function's behavior and boiling it down to just its values at very specific points.
Yep.
But then, the big question is, under what conditions does this hold in other spaces?
Yeah.
Right, for different kinds of functions.
Exactly. And that's what, Kolomoitsev and Tikhonov set out to explore in this paper.
Right, and so then they move on to pages 3 through 7, where they look at boundedness of maximal and minimal functions.
Right.
Which I guess this is where theorem 2.1 comes in.
Yeah, this is really a key theorem. It shows that if you have a Bernstein-type inequality in your space that bounds the derivative of your function, then you can actually control the maximum and minimum values that function can take within a certain cube.
Okay, hold on. So we're not talking about just points anymore. We're talking about regions of space.
Exactly. We're looking at, sort of localized regions. Yeah.
Yeah.
And the size of these cubes is determined by this parameter n and this constant a, and they can't be arbitrarily large. Remark 2.2 shows this quite nicely. It shows that if you have a function like a sin and you try and look for its minimum in a cube that's too big,
right,
you're just going to get 0.
Of course.
Yeah, so you need to kind of zoom in to the right level.
It's like we're looking for peaks and valleys.
Exactly. Yeah. Now, theorem 2.1 is great because it can be extended to quasi-Banach spaces, and it can even incorporate these weighted Bernstein inequalities, which is theorem 2.6.
Okay.
And this allows us to handle even non-periodic functions on bounded domains, which is really cool.
Great.
And remark 2.8 kind of illustrates this nicely with algebraic polynomials on Nagiluan 1. And in this case, this weight function is related to the distance from the endpoints.
Okay.
So it's like we're customizing our tools to fit the function in the space.
I like that. So then what happens?
Okay, so then we move to pages 8 and 9, where they introduce these general MZ inequalities. This is theorems 2.9 and 2.9 around. And these give us a sort of framework for proving these MZ inequalities in all sorts of different settings. And they use these carefully chosen sets, AC and AC, that satisfy certain geometric conditions related to the space and the function class that we're looking at.
So it's almost like we're setting up a stage, and then we're going to pick our actors to come on.
I like that. Yeah, it's like a blueprint for constructing these inequalities.
And then we get to pages 9 through 12, where they start talking about MZ inequalities with a minimal number of nodes, which sounds pretty cool.
Yeah, it's all about efficiency, right?
Yeah.
And this is where they introduce this concept of using quadrature formulas to derive these inequalities.
Okay.
And theorem 3.1 is kind of the key theorem here. Quadrature formulas are great. They allow you to calculate the exact integral of a polynomial by just summing up its values at specific points.
Wow.
Using appropriate weights.
So instead of having to integrate over the whole area, we just pick a few points.
Exactly. It's a beautiful shortcut. But there are some conditions that need to be met. Theorem 3.1 outlines these 5 key conditions. We need a suitable quadrature formula. We need the boundedness of the Fourier partial sums in the space.
Right.
We need a weighted Bernstein inequality. And then we need these geometric conditions on the sets.
Sounds like a checklist.
Exactly. It's a recipe for success.
Nice. Now, before we move on, I think we need to go back to Theorem 2.1, the one about the maximum and minimum and like bounding those.
Okay.
Because the proof in the paper is pretty elegant.
Yeah.
And it's nice to see like how those Bernstein inequalities really are the key to the whole thing.
Okay, so the proof starts by considering a function f in our space, and we want to control its maximum and minimum values inside of this cube Q, whose side length is n is related to like the degree of the polynomial approximation of f, and a is some constant. Now the key idea is to introduce this auxiliary function g, which is defined as the convolution of f with the smooth bump function.
Okay.
Supported on a smaller cube Q inside of Q.
So why are we even doing this? Like, what's the strategy here?
Right. So the strategy is really quite clever. By choosing very carefully, we can ensure that G is a nice smooth approximation of F inside of Q. And also, because G is smooth, we can apply the Bernstein inequality to its derivatives.
Ah, so we're using the smoothness of G to bring in the Bernstein inequality.
Exactly. And since G is close to F inside of Q, the maximum and minimum values of F inside of Q can be estimated by just looking at the values of G and its derivatives at the center of Q.
Okay, so we've transferred the problem from F to G. Which is easier to work with because it's smooth.
Exactly.
Now we can use Bernstein.
Exactly. Now we use the Taylor expansion of G around the center of Q. We can express the maximum and minimum values of G in terms of its derivatives at the center. And then since we have this bound on the derivatives from the Bernstein inequality, we get the bounds that we want on the maximum and minimum values of F.
Okay.
Yeah. So the Bernstein inequality is really the key, along with this clever choice of G. And this is really fundamental because it allows us to derive these more general MZ inequalities.
Okay.
This ability to control the local behavior of the functions using these Bernstein type inequalities is what allows us to kind of connect the continuous and the discrete.
Awesome.
Yeah. Now, let's see. Pages 12 through 23 is where they start applying this general framework to some familiar families of functions. First, they look at trigonometric polynomials and then algebraic polynomials.
So now we're getting into like specific cases.
Exactly, yeah. So for trigonometric polynomials, theorem 4.1 is the main result. It establishes this MZ inequality with a minimal set of nodes. Provided that the Fourier partial sum operator is bounded in the space that we're working in. Which
makes sense, given that it's, Fourier,
Yeah. And then for algebraic polynomials, things get a little bit more tricky.
Okay.
And they provide 2 different approaches.
Okay.
Theorems 5.2 and 5.5. Theorem 5.2 uses this Markov inequality, which gives us a bound on the derivative of the polynomial.
So we're using information about how fast it can grow.
Exactly.
To help us.
Exactly. And this allows us to establish an MZ inequality for rearrangement invariant Banach lattices.
Which I assume have some special properties that make this approach work.
You're exactly right. Yeah, rearrangement invariant spaces, the norm is unchanged if you just rearrange the values.
Okay.
So
interesting. What about theorem 5.5?
Okay, so theorem 5.5 brings back these quadrature formulas.
Okay.
Are shortcuts for calculating integrals.
Right, right.
And they use these to derive an MZ inequality.
Okay.
With a minimal number of nodes for algebraic polynomials.
So we've got like different tools that we
Yeah.
can apply to different,
Exactly.
if it's trigonometric, we can use Fourier stuff.
Yeah.
If it's algebraic, we can use these, Markov or quadrature.
Exactly. And, this versatility is what makes this area of research so interesting.
So then on pages 23 to 25, they go beyond polynomials.
Right.
And they start looking at other function classes.
Right. They look at band-limited functions,
Okay.
splines, exponential sums, and even Manwin's polynomials.
Wow. Okay, so we're going on a little tour here.
Yeah, it's a
Right.
it's a whole zoo of functions.
What are band-limited functions?
So band-limited functions are they have a limited range of frequencies in their Fourier transform. So they're very common in signal processing and things like that. It turns out that the results that they get for these functions are very closely related to the classical Plancherel Polya inequality.
So it's like we're filtering out
Yeah.
the high frequencies, the stuff that we don't need.
Exactly. Yeah.
Okay, and what about splines?
Okay, so splines are, these piecewise polynomial functions. They're used a lot in approximation, computer graphics, things like that. They're like mathematical Legos.
Okay.
You can build up smooth curves and surfaces out of these things.
And how do these MZ inequalities apply to them?
Right. So for splines, the key is a Bernstein-type inequality that's specific to these piecewise polynomials. It allows you to control the behavior of the spline within each of these pieces,
Okay.
and that allows you to derive this MZ inequality
Right.
for the whole spline.
So we're adapting our tools again
Exactly. Yeah.
to fit the splines. Now, what about these exponential sums and mean-Newton's polynomials?
Okay, so exponential sums are just, linear combinations of exponential functions.
Oh.
They have applications in approximation theory, number theory, all sorts of things. Min's polynomials are similar, except that the exponents can be non-integer values.
Okay.
And in both cases, this quantity plays an important role. It sort of incorporates information about the exponents
Right.
and the degree of the polynomials.
So we're really kind of looking at the structure
Yeah.
of these functions. But
Yeah.
I mean, okay, this is all very interesting from a theoretical standpoint,
Yeah.
but like why should we care?
That's the million-dollar question.
Yeah.
And the authors address that on pages 25 through 31.
Okay.
They highlight several applications of these MZ inequalities,
Okay.
focusing on things like approximation by sampling operators, Nikolskii inequalities, and then inequalities for best approximations and moduli of smoothness. So really showcasing the impact of these inequalities on how we represent, approximate, and analyze functions.
Okay, so let's go through those
Right.
one by one because I want to make sure we understand like the so what here. Like
Right.
why are we doing this?
Okay.
So approximation by sampling operators.
Okay, so this is subsection 7.1. This is really, really relevant to our, our digital world today.
Yes.
Where, we're always dealing with these discrete representations of continuous information.
Right.
And this section shows how these MZ inequalities give us tools to analyze the accuracy of these approximations.
Okay.
They allow us to derive error estimates for when we use interpolation methods to reconstruct a function from its sample. So it tells us, what's the trade-off between accuracy and the number of samples that we're using.
So if I'm compressing a JPEG,
Exactly.
it can tell me how much information I'm losing.
Exactly.
Okay, cool.
Yeah.
What about Nikolskii inequalities?
Okay, so Nikolskii inequalities, this is subsection 7.2. These are really fascinating inequalities. They relate the norms of polynomials in different LP spaces.
Okay.
So it's like, if you're measuring the length of something,
Yeah.
do you use inches or centimeters?
Right. The number changes, but
Yeah, exactly.
the thing is the same.
Exactly. So, and the remarkable thing is that the MZ inequalities, they provide a bridge
Okay.
to these classical Nikolskii inequalities.
So we're connecting these two concepts.
Exactly.
Okay, cool. And then the last one.
Right. So the last one, subsection 7.3, this is about inequalities for best approximations and moduli of smoothness.
Okay.
So these concepts are really fundamental to understanding, like, how well can we approximate a function?
Yeah.
Using, simpler functions, and, how smooth a function is in a precise mathematical sense.
Right.
Right. So if you're trying to, model some complex physical phenomenon using a simple mathematical function, These inequalities can tell you, what are the inherent limitations of your model?
Okay.
How accurately can you capture the true behavior?
Right.
And the fascinating thing is that the MZ inequalities, they play a key role
Yeah.
in establishing these connections.
Okay.
They provide this unifying framework for understanding approximation and smoothness.
Very cool. Now, before we move on, I do want to go back to theorem 3.1.
Okay.
Because we kind of glossed over it.
Yeah.
But it is pretty amazing how these quadrature formulas can give us these minimal, nodes.
Right.
So can we dive into that a little bit more?
All right. Yeah. So theorem 3.1 is really a recipe for constructing these efficient MZ inequalities.
Okay.
The first ingredient, of course, is a suitable quadrature formula. And this allows us to approximate the integral of a function using a weighted sum of its values at a specific set of points. And we call these points the nodes.
So we're carefully choosing these points and assigning them weights.
Exactly.
To be able to capture the integral.
Exactly. Yeah. Now, the second ingredient is the boundedness of the Fourier partial sum operator in our space. And this ensures that we can control the behavior of the function using its Fourier representation. It's like saying, we can understand the function by looking at just a finite number of its frequency components.
Okay, that makes sense.
Yeah.
As long as it's not too crazy.
Exactly. And then the third ingredient is a weighted Bernstein inequality. And this inequality is tailored to the specific function class that we're dealing with.
Okay.
And it allows us to control the growth of the derivatives of the function.
Okay.
It connects the smoothness of the function to its behavior at different points.
So if it's smooth, it can't be too crazy.
Exactly. Yeah. And then finally, we need some specific geometric conditions on these sets that we're using to construct our sampling points. And these ensure that our points are kind of distributed effectively throughout the domain.
So it's all about the placement of the points and the number of them and the weights that we assign.
Exactly. And when all of these ingredients come together just right, Theorem 3.1 guarantees that we can derive an MZ inequality with a minimal number of nodes.
Okay.
So it's really a very efficient way to connect the continuous and discrete aspects of the function. It's
amazing that these quadrature formulas can do that.
It is really quite remarkable.
Can we talk about some specific quadrature formulas?
Oh, sure. Yeah, there's a whole bunch of them out there.
Right.
Some popular choices include the Newton-Cotes formulas, like the trapezoidal rule and Simpson's rule. These are, relatively simple to implement. And then you have Gaussian quadrature formulas, which are known for being very accurate and efficient, especially for integrating smooth functions.
So it's like choosing the right tool for the job.
Exactly. Yeah. The choice of the quadrature formula often depends on the function that you're integrating and the desired level of accuracy.
Okay.
So, for example, if you're, dealing with a function that's highly oscillatory or has, some singularities, you might want to use, a Gaussian quadrature formula.
Okay.
But how do we know, which quadrature formula is suitable?
Yeah, how do we know which one to pick?
Yeah, so that's a great question. The suitability of a quadrature formula in this context really depends on a few factors. The function class that we're working with, the space that we're considering, and the geometric conditions on our sampling sets. So, for instance, if you're working with trigonometric polynomials, quadrature formulas that are based on equally spaced nodes, often work quite well because of the periodic nature of these functions. But if you're dealing with algebraic polynomials, you might need to consider quadrature formulas where the nodes are distributed differently. Like the Chebyshev nodes. Which are known for their good approximation properties for polynomials.
So there's this interplay between the functions, the space, and then the geometry of the nodes.
Exactly. It's a really fascinating area of research. And it has deep connections to all sorts of different areas of math, approximation theory, numerical analysis, and even number theory.
It's really incredible how much comes out of this idea of sampling.
It really is.
Like just picking points.
Yeah.
It seems so simple, but But all this stuff comes out of it.
Yeah, and we've just scratched the surface, really. The world of MZ inequalities is vast and full of surprises. And as we move into, looking at their applications, we'll see how these connections can really be used to solve real world problems and to gain these deep insights into the behavior of functions.
Excellent. Okay, so, wow, we just went through like a whirlwind tour of functional analysis.
Yeah.
I feel like my brain is a little bit fried, but
It's good, though.
But in a good way.
Yeah, it's invigorating to see.
It is.
How these, seemingly simple ideas can lead to such profound insights.
Absolutely. So we've covered a lot of ground with these Marcinkiewicz-Zygmund inequalities. We started with the classical ones, we went to the modern extensions, all the applications.
Right. We started with this fundamental idea of relating the norm of a function to the norm of a simpler function that's constructed from its samples. And we saw this beautifully in equation 1.2 for these trigonometric polynomials in these LP spaces.
Right.
And then we ventured into, this realm of Banach and quasi-Banach function spaces, guided by theorems 2.9 and 2.9, which gave us this general framework for proving these MZ inequalities in these different settings.
Right. And along the way, we talked about Bernstein inequalities, quadrature formulas.
Right.
How to adapt all these things to different function classes.
Exactly. Yeah. We saw, those algebraic polynomials, band-limited functions, splines, and even those, more exotic exponential sums and Munitz polynomials.
Right. We even got into the weeds a little bit.
Yeah.
With quadrature formulas, which are, I don't know, I kind of love those.
Yeah, they're great. They're like these shortcuts for calculating integrals. And we saw how they can be used to derive these really efficient MZ inequalities.
But now we need to step back and talk about the so what.
Right.
Like why did we spend all this time looking at these things?
Right. So Kolomoitsev and Tikhonov, they showcase several applications.
Sure.
Focusing on these three main things: approximation by sampling operators, Nikolskii inequalities, and then inequalities for best approximations and moduli of smoothness.
Okay, so let's go through those one by one.
Okay.
What about approximation by sampling operators?
Okay, so this is subsection 7.1. And this is very relevant, in today's world where we're constantly dealing with these discrete representations of continuous information.
Right.
And this section shows how these MZ inequalities give us these tools to analyze how accurate these approximations are.
Okay.
And they allow us to derive these error estimates when we use these interpolation methods to reconstruct a function from its samples.
Right.
So it tells us, how much accuracy are we sacrificing when we only use a certain number of samples.
So like the JPEG example again.
Exactly.
Like how much are we losing by compressing it? Okay, what about Nikolskii inequalities?
Okay, so Nikolskii inequalities, this is subsection 7.2.
Yeah.
These are fascinating inequalities. They relate the norms of polynomials in different LP spaces. So it's like, you're measuring the length of something, and you're asking, should we use inches or centimeters?
Right. The number changes, but the actual length.
Exactly.
Yeah.
And what's amazing is that MZ inequalities provide this bridge to these classical Nikolskii inequalities.
Okay, so we're showing a connection between these concepts.
Exactly.
Okay. And then the last one.
Right. So the last one, subsection 7.3, this is about inequalities for best approximations and moduli of smoothness.
Okay.
And these are really key concepts for understanding, how well can we approximate a function using a simpler function, and how smooth is a function in a very precise, mathematical sense.
Right. If I'm trying to model something with math, I want to know how good my model is.
Exactly. And these inequalities tell you that. They tell you what are the limitations of your model. How accurately can you capture the behavior? Right.
And MZ inequalities, they play a role in all of this.
Exactly. Right. They provide this unifying framework for understanding approximation and smoothness.
So it's like this common thread that ties all these things together.
Exactly.
Very cool. Well, I think this has been a very fascinating deep dive into the world of Marcinkiewicz-Zygmund inequalities. We've seen how this simple idea, just, sampling a function,
Yeah.
can lead to, all these really interesting results, connecting all these different areas of math
Yeah.
and giving us tools to solve real-world problems.
Exactly.
So I encourage our listeners, keep exploring. You never know what you're going to find. There might be an application of these MZ inequalities hiding somewhere
Yeah.
in your own work.
Exactly.
And even if not,
Yeah.
it's just beautiful math.
Yeah.
And it's always great to see how these things connect.
Absolutely. The more we explore, the more we see how interconnected and how beautiful it all is.
Absolutely. Thanks for joining me on this deep dive.
Oh, it's my pleasure.
All right, ready to dive into some Marcinkiewicz-Zygmund inequalities.
Yeah, let's do it.
Cool. Specifically, this paper on these inequalities in quasi-Banach function spaces. I'm really curious about how these inequalities, like how they work beyond the familiar LP spaces.
Yeah, it's fascinating, isn't it? This whole idea of bridging, the continuous and discrete representations of functions.
Yeah.
It's like we're using like a finite or even like a countable set of points
All right.
to get a grasp on how the function behaves like in this much larger space.
Right. It's like we're trying to just get the essence of the function, just from a few like carefully chosen values. And I see this paper, it starts with that classic Marcinkiewicz-Zygmund inequality, for those trigonometric polynomials.
Right, exactly. Equation 1.1, it really lays the groundwork here.
Okay.
It basically says that you've got a trigonometric polynomial, we'll call it T, and its degree is at most n. Its LP norm, it can be bounded both, above and below by these sums that use its values at like these equally spaced points.
Okay.
You know what I mean? Specifically, we've got, hold on, let me find it. Okay. Yeah, equation 1.1. It's
Okay.
TAOP Franoan plus one sum Kio EPO.
Okay, I see.
Where the TOAs, those are the equally spaced points, around the circle.
Right, right.
Yeah.
So we're basically saying that the size of the polynomial, like as measured by its LP norm,
Yeah.
you can kind of estimate that just by looking at its values at these very specific points.
Exactly.
And I guess the approximation, like the better it gets, the more points you use, right?
Precisely, yeah. And what's really neat is how they rewrite this inequality in equation 1.2
Okay.
to highlight this connection to interpolation with a simple function.
Okay, I'm curious about that.
Yeah.
Can you break that down for me a little bit?
Sure, yeah.
Like, how does interpolation even come into play here?
Okay, so they introduced this like simple function. We can call it Tauer-Jollers. And it basically what it does is it takes on the values of our polynomial T at those equally spaced points, and then it's just constant between them.
Okay, yeah.
And equation 1.2, it shows that. Approxy in TSP.
Got it.
So this shows that the LP norm of our original polynomial, it's basically the same as the LP norm of this like simple piecewise constant function that like interpolates it.
So we're approximating the polynomial with a simpler function.
Exactly.
One that kind of captures its behavior at those key points.
Right.
But then I guess the real challenge, it's figuring out how these inequalities, like how they generalize to more abstract spaces.
Exactly, yeah. The paper, it dives into Banach and quasi-Banach function lattices, which are like way broader than just your regular LP spaces. And that's where things get really interesting.
Okay, so then how do we even begin to tackle these Marcinkiewicz-Zygmund inequalities in these more general settings?
Well, the paper, it brings in this concept of maximal and minimal functions.
Okay.
These play like a really key role.
Can you explain what those are and why they're so important in this context?
Yeah, so imagine you have a function and you want to understand like what it's doing locally. The maximal function, which we denote by MF, it basically captures the largest value that the function takes within a small neighborhood around each point.
Oh, okay.
So it's like we use this formula, MFX supraphi 1 BX SY die.
Okay.
Here, BX4 is like a ball centered at X with radius R.
Okay.
And we're just taking like the average value of the absolute value of F within that ball.
Right.
And then the minimal function, we call it MF, it does the opposite.
Yeah.
It captures the smallest value.
Got it.
So that formula is
fx, mfx, or in for nice y.
Yes.
So it's like zooming in on the function at each point and like looking for like the highest peak or the lowest value within a small window.
Exactly. Yeah, that's a great way to put it. And then theorem 2.1, this is where it gets interesting.
okay.
This theorem, it connects these like local features to the global norm of the function. In a translation invariant Banach lattice, it says that under certain conditions, you have this. Approx and
Approx. So the norm of the function, it's comparable to the norms of its maximal and minimal functions.
Yeah.
But what are those conditions?
Well, one that's super important is the Bernstein inequality.
Okay.
It basically says that for functions in a specific subspace, the norm of their derivative, it can be bounded by like a constant times the norm of the original function, all scaled by the degree of the function, you know? Yeah. That makes sense. But the smoother the function, the slower its derivatives can grow, right?
Right, exactly.
And that should translate into better control over its overall behavior.
Exactly, yeah. But there's a subtle point here highlighted in remark 2.2.
Okay.
The size of those little balls, you know those neighborhoods we used to define the maximal and minimal functions?
Yeah.
That matters. Like you can't just make them arbitrarily large and still expect these inequalities to hold up.
So it's like a delicate balancing act, right? To capture the local behavior in a way that accurately reflects the global properties of the function.
Exactly. And this sets the stage for some really interesting generalizations.
Okay.
Like theorem 2.6, for example, this one extends these ideas to quasi-Banach spaces.
Okay.
Which are even more general than Banach spaces.
Right.
But to make it work, they have to introduce a weighted version of the Bernstein inequality.
Okay. So we're adding in like another layer of flexibility with these weight functions.
Yeah.
Can you give us like a sense of what they do and why they're needed?
Imagine you're working with functions on a bounded interval, like algebraic polynomials.
Go.
The classical Bernstein inequality, it might not be like sharp enough in this case. The weight function, it acts like a lens, you know? Focusing the inequality on the specific behavior of the function in different parts of the interval.
So instead of having like a uniform constraint on the derivatives, we're allowing for like a more tailored approach, you know?
Exactly, yeah.
That adapts to the function's like local properties.
Right, exactly. And remark 2.8, it gives a concrete example, you know, showing how this weighted Bernstein inequality relates to the classic Markov inequality for algebraic polynomials on convex domains.
So we're starting to build like a toolbox of inequalities, right?
Yes.
That capture the behavior of functions in these increasingly complex settings.
Yes.
So what happens next?
Well, the paper, it then tackles, you know, the general Marcinkiewicz-Zygmund inequalities in theorems 2.9 and 2.10.
Okay.
These theorems, they lay out the conditions, you know, under which we can estimate the norm of a function in these like general spaces based on its values at a collection of points which don't even have to be finite.
Infinitely many points. That's wild. How can we possibly like handle that?
The key is it's all in the conditions.
Right.
Especially those conditions 2.1 to 2.14.
Okay.
They make sure we can effectively, you know, cover the whole domain with sets like AIK,
right,
while still making sure we're meeting the requirements for those maximal and minimal function bounds. It's like a carefully, you know, choreographed dance or something.
Yeah.
To make sure that our sampling strategy, even with infinitely many points, gives us like reliable information about the function.
Okay. This is all incredibly fascinating, but my mind's starting to feel a bit stretched, I gotta say.
Yeah.
Can we maybe pause here for now?
Sure, yeah.
And pick up the rest of the discussion in part 2.
Sounds good. We've laid a good foundation.
Yeah.
And next time we can get into that exciting world of minimal nodes,
right,
quadrature formulas,
okay,
and the specific applications of these powerful inequalities.
Awesome. Looking forward to it.
Yeah. Welcome back. Ready to keep going with these Marcinkiewicz-Zygmund inequalities.
Yeah, let's jump right back in.
All right. Last time we saw how these inequalities, you know, capture the essence of a function's behavior using a well-chosen set of values.
Right. Even in those abstract spaces like Banach and quasi-Banach lattices.
Yeah, exactly.
And it was fascinating to see how, like those tiny peaks and valleys of a function captured by the maximal and minimal functions, how they can actually tell us so much about its global behavior.
Exactly. Ready to dive into the world of minimal nodes? See how we can achieve these inequalities with like maximum efficiency?
Absolutely. I mean, the idea of using the fewest points possible to capture the essence of a function, that sounds incredibly powerful.
It is, and that's where quadrature formulas come in.
Okay.
These formulas, they let us approximate integrals, using a weighted sum of function values at like these specific points, the nodes.
Right.
The trick is picking those nodes carefully to like maximize the accuracy of the approximation.
So instead of needing to know the function's value everywhere, we can pick just the right points to really capture its behavior, huh?
Exactly.
That's brilliant. But how do we actually find those magic nodes?
Theorem 3.1, that's the key.
Okay.
It shows that if you have a quadrature formula and it exactly integrates products of functions from a certain subspace, then you can actually achieve a Marcinkiewicz-Zygmund inequality using those quadrature nodes.
I'm starting to see the connection here. We're essentially using the accuracy of the quadrature formula to kind of guarantee the accuracy of our norm estimate.
Yeah.
Based on those nodes.
Exactly.
But can you maybe give me like a concrete example?
Sure.
Of how this works in practice?
Yeah, let's look at section 3.2. This one focuses on Orless spaces.
Okay.
These spaces, they're a generalization of LP spaces.
Right.
And they give you more flexibility in controlling how different function values contribute to the overall norm.
Right. We touched on Orless spaces a little bit before.
Yeah.
Can you remind me why they need like special treatment?
Yeah, so in some cases, that standard LP norm, it might not be sensitive enough to capture the subtle nuances of the functions we're working with.
Right.
Orless spaces, they give us a more like refined way to measure the size of a function.
So it's like we're fine-tuning the lens through which we view these functions, right?
Yeah. Exactly, yeah. Now, the tricky part with Orlich spaces is that those classic translation operators, they might not behave as nicely as they do in LP spaces.
Right.
To deal with this, the paper introduces this concept of generalized translation operators.
So we need new tools to navigate these more complex spaces.
Exactly. And theorem 3.3, this one shows how those generalized translations combined with a specific kernel function, like the Eldevale-Poussin type, can be used to establish a Marcinkiewicz-Zygmund inequality in this setting.
Okay, so I'm starting to see how each type of function space seems to demand like its own unique approach and set of tools.
You got it.
To really unlock those Marcinkiewicz-Zygmund inequalities.
Exactly, yeah. Ready to see how all this plays out in some concrete examples.
Absolutely. Let's bring those abstract theorems to life.
Okay, so the paper starts with trigonometric polynomials.
Okay.
This is in section 4. Remember those equally spaced points we used in the classic Marcinkiewicz-Zygmund inequality?
Yeah. Well, theorem 4.1, it shows that for certain Banach lattices, like some Orlitz spaces, we can actually get an exact equivalence between the norm of a trigonometric polynomial and a sum based on its values at those same points.
So those equally spaced points, they're not just like a convenient choice. They're actually optimal in some cases.
You got it.
Wow.
Yeah. And this really shows the deep connection between the structure of the function space,
right,
and the best choice of nodes for the Marcinkiewicz-Zygmund inequality.
Okay, that's incredibly cool. What about algebraic polynomials?
Okay.
How do things change when we move from that periodic world of trig functions to like the more general realm of polynomials?
That's where section 5 comes in.
Okay.
And this is where we hit a fascinating twist. That classical Bernstein inequality that worked so well for trig polynomials.
Yep.
It's not as sharp for algebraic polynomials, especially on bounded intervals.
Yeah.
So we need a new tool for the job.
Exactly. The paper, it turns to the Markov inequality.
Okay.
This one gives a more precise bound on the growth of derivatives for algebraic polynomials, especially on those bounded intervals.
Right.
Proposition 5.1, this one extends the Markov inequality to a broader class of spaces, those rearrangement invariant Banach lattices.
So instead of relying on the translation invariance we had with trig polynomials,
Yeah.
we're using the specific properties of these rearrangement invariant spaces to get our bounds on.
Precisely. And with this new tool, we can establish Marcinkiewicz-Zygmund inequalities for algebraic polynomials in these spaces.
Okay.
Theorem 5.2, this one shows that for a rearrangement invariant Banach lattice on an interval, like AB, you can estimate the norm of a polynomial just by looking at its values at a specific set of points.
Okay, but are these points still like equally spaced?
Not always, no.
Okay.
This is where it gets interesting. The optimal choice of nodes for algebraic polynomials, it's often tied to the weight function that's associated with the Markov inequality.
Ah, so the weight function is playing a bigger role here.
Yeah.
Can you maybe say a little more about that connection?
Sure. Imagine you have a weight function that, it emphasizes certain parts of the interval.
Right.
Maybe it gives more weight to the unpoints.
Okay.
The best nodes for the Marcinkiewicz-Zygmund inequality, they'll often cluster in those regions where that weight function is larger.
So it's like the weight function is kind of guiding us toward the most informative points.
That's right.
To capture the polynomial's behavior.
And this interplay between the weight function and the choice of nodes, it becomes even clearer in section 5.2.
Okay.
This is where the paper introduces a refined version of the Bernstein inequality,
Right.
specifically for algebraic polynomials on the interval Nakrivol-Nakado 1.
Right. You mentioned this before. Why focus on that interval?
It's partly for convenience.
Okay.
And partly because that interval, it's often used as like a standard domain for studying algebraic polynomials.
Okay.
A lot of the results can be generalized to other intervals through like simple transformations.
Right.
But what's really important here is that the weight function they use in this refined Bernstein inequality, it's designed to capture how polynomials behave near the endpoints of this interval.
So we're dealing with a weight function that's really sensitive to the like peculiarities of how polynomials behave at the boundaries. Huh?
Exactly. Yeah.
Interesting.
And this lets us establish these Marcinkiewicz-Zygmund inequalities that are more accurate and efficient, especially when we choose the nodes to reflect how this weight function influences things.
It's like we're placing those nodes with like surgical precision,
Exactly. Yeah.
to extract like the most information possible.
Example 5.4, this illustrates this really well.
Okay.
It looks at Marcinkiewicz-Zygmund inequalities for weighted LP spaces on -1, 1. And they don't just pick any nodes, they use the zeros of Chebyshev polynomials, which have some really cool properties that line up perfectly with the weight function being used.
Okay, I'm seeing a pattern here. It seems like whenever we bring in a weight function,
Yeah.
the choice of nodes seems to be like really closely tied to its structure.
You got, yeah, it's like a mathematical dance between the weight function, the nodes, and those Marcinkiewicz-Zygmund inequalities.
Now remember how we were talking about using like the fewest points possible?
Yeah, yes.
What happens when we're trying to get that maximum efficiency with algebraic polynomials?
That's where section 5.3 comes in.
Okay.
This is where they introduce theorem 5.5. This one focuses on achieving Marcinkiewicz-Zygmund inequalities using like the absolute minimum number of nodes for algebraic polynomials.
Minimal nodes, maximum insight.
Exactly. And guess what plays a crucial role in this theorem?
Quadrature formulas.
Quadrature formulas, you got it.
Nice.
Those formulas, they give us a way to approximate integrals using a weighted sum of function values at specific points.
Yeah.
And when you choose those points right, you can get these really accurate estimates with very little effort.
So it's like we're boiling down that polynomial's behavior to just a handful of strategically placed points.
Exactly. And in theorem 5.5, those special points, they turn out to be the zeros of orthogonal polynomials associated with the weight function that defines our space.
Right.
Like it all comes full circle. The weight function, the orthogonal polynomials, those Marcinkiewicz-Zygmund inequalities, they all work together.
It really is like a mathematical symphony.
Yeah.
Each element playing its part to create this beautiful and efficient result.
Exactly. Now, if you thought that was impressive, the paper doesn't stop there. It goes on to explore Marcinkiewicz-Zygmund inequalities for other function classes, too.
like band-limited functions,
Yeah.
splines, exponential sums, even means polynomials.
Wow, it's like these inequalities, they have this universal appeal, huh?
Yeah, they really do.
Extending far beyond just polynomials.
Yeah, and the cool thing is while the specific, tools and techniques, they might change depending on what function class we're working with.
Right.
The underlying principles, they stay the same.
So it's like having like a master key,
Yeah.
to unlock this treasure trove of mathematical knowledge.
Exactly.
And it's adaptable to all these different situations.
That's a great way to put it. And to bring it all back around, the paper then gets into some of the really amazing applications of these inequalities in section 7.
Okay, what kind of applications are we talking about here?
Well, one area where they really shine is approximation theory. Like understanding how accurate different methods are for approximating functions using, simpler building blocks.
Okay.
They also show up in signal processing, numerical analysis, even some areas of theoretical physics.
Wow, it's like we stumbled upon a mathematical Swiss Army knife or something.
Yeah, they're incredibly versatile. For example, the paper shows how you can use Marcinkiewicz-Zygmund inequalities to figure out error estimates for sampling operator.
Okay.
Like that classic Lagrange interpolation, for example.
Right.
They also lead to some really elegant proofs of some key inequalities in approximation theory, like the Nikolskii inequalities, which connect the norms of a function in different spaces.
So not only are these inequalities powerful on their own, but they also act as like this unifying thread, right?
Yes.
Connecting all these different concepts and results across different fields of math.
Exactly. And that's what makes them so interesting to study.
Okay, so picking up where we left off, we've been talking about Marcinkiewicz-Zygmund inequalities and how they give us this powerful way to like estimate the norm of a function. And we only need to look at a carefully chosen sample of its values, even in these abstract spaces like Banach and quasi-Banach lattices.
Exactly.
And we were diving into algebraic polynomials, which is where things start to get like really interesting.
Yeah, definitely.
We saw how that classical Bernstein inequality, the one that works so well for trigonometric polynomials,
right.
It's not quite as sharp for algebraic polynomials, especially on those bounded intervals.
You got it.
And you mentioned the Markov inequality as like a more precise tool for this setting.
Precisely. The Markov inequality gives us a sharper bound on how fast those derivatives can grow for algebraic polynomials. And what's really neat is proposition 5.1 in the paper. It extends the Markov inequality to those rearrangement invariant Banach lattices.
So we're basically leveraging those properties of these spaces to gain better control over the behavior of these algebraic polynomials. Right?
Yeah.
But how does this translate into actual Marcinkiewicz-Zygmund inequalities?
Well, theorem 5.2, this shows that for a rearrangement invariant Banach lattice on an interval like a, b, we can estimate the norm of an algebraic polynomial just by looking at its values at a specific set of points.
Okay, but are those points still equally spaced like they were for those trigonometric polynomials?
Not necessarily, no. This is where it gets really interesting. The best choice of nodes for algebraic polynomials, it's often tied to the weight function that's associated with the Markov inequality.
So the weight function is playing a more significant role here. Can you elaborate on that connection a little bit?
Yeah, sure. Imagine you have a weight function that emphasizes certain parts of the interval, like maybe gives more weight to the endpoints. The best nodes for that Marcinkiewicz-Zygmund inequality, they'll often cluster in those regions where the weight function is larger.
So it's like the weight function is kind of like guiding us, toward the most informative points for really capturing the behavior of that polynomial.
Precisely. And this interplay between the weight function and how we choose the nodes, it becomes even more apparent when we look at section 5.2. This is where they introduce a refined version of the Bernstein inequality tailored specifically for algebraic polynomials on that interval, Mach 1, 1.
Right. You mentioned this before. Why focus on that specific interval? Is it just for convenience, or is there something special about it?
It's a bit of both. The interval of Mach 1, 1, it's often used as like a standard domain, for studying algebraic polynomials, because a lot of those results can be generalized to other intervals through simple transformations.
Okay.
But what's key here is that the weight function they use in this refined Bernstein inequality, it's specifically designed to capture the behavior of polynomials near those endpoints of the interval.
So we're dealing with a weight function that's really sensitive to like the peculiarities of polynomial behavior at those boundaries.
Exactly. Okay, cool. And this lets us establish Marcinkiewicz-Zygmund inequalities that are more accurate and efficient, especially when we pick the nodes to reflect how this weight function is influencing things.
It's like we're placing those nodes with like surgical precision.
Exactly.
To extract the most information possible.
Example 5.4, this illustrates this really well. It looks at Marcinkiewicz-Zygmund inequalities for weighted LP spaces on -1, 1, and they don't just pick any old nodes. You know, they use the zeros of Chebyshev polynomials, which have some really cool properties that line up perfectly with that weight function.
Okay, so I'm seeing this clear pattern here. Like whenever we introduce a weight function, the choice of nodes, it seems to be really like intimately linked to the structure of that weight function.
Absolutely. It's like a mathematical dance between that weight function, the nodes, and those Marcinkiewicz-Zygmund inequalities all working together.
Now remember how we talked about using the fewest points possible.
Right.
What happens when we try to achieve that maximum efficiency in the context of algebraic polynomials?
That's where section 5.3 comes in. This is where they introduce theorem 5.5, which focuses on achieving Marcinkiewicz-Zygmund inequalities using the absolute minimum number of nodes for algebraic polynomials.
Minimal nodes, maximum insight. I love it.
Exactly. And guess what plays a key role in this theorem?
Quadrature formulas.
Quadrature formulas, you got it. Those formulas give us a way to approximate integrals using a weighted sum of function values at specific points. And when we choose those points carefully, we can get these incredibly accurate estimates with very little effort.
So it's like we're boiling down the polynomial's behavior, like distilling it down to just a handful of strategically placed points.
Precisely. And in theorem 5.5, those special points, they turn out to be the zeros of orthogonal polynomials associated with the weight function that defines our space. So it's like it all comes full circle. The weight function, the orthogonal polynomials, those Marcinkiewicz-Zygmund inequalities, they all work together.
It really is like a mathematical symphony, each element playing its part to create this beautiful and efficient result.
Exactly. Now, if you thought that was impressive, well, the paper doesn't stop there. It goes on to explore these Marcinkiewicz-Zygmund inequalities for other function classes, too, like band-limited functions, splines, exponential sums, even those Minet's polynomials.
Wow, it's like these inequalities have this universal appeal, huh? Extending far beyond just polynomials.
They really do. And what's really cool is, while the specific tools and techniques might change depending on the function class we're working with, the underlying principles, those remain the same.
So it's like we've got this master key, to unlock this treasure trove of mathematical knowledge, and it's adaptable to all these different situations.
That's a great way to put it. And to bring it all back around, the paper then looks at some of the really amazing applications of these inequalities in section 7.
Okay, what kind of applications are we talking about here?
Well, one area where they really shine is in approximation theory, like understanding how accurate different methods are for approximating functions using simpler building blocks. They also pop up in signal processing, numerical analysis, even in some areas of theoretical physics.
Well, it's like we stumbled on this mathematical Swiss Army knife.
They're incredibly versatile, yeah. For example, the paper shows how we can use these Marcinkiewicz-Zygmund inequalities to figure out those error estimates for sampling operators, like a classic Lagrange interpolation, for instance.
Okay.
They also lead to some really elegant proofs of some key inequalities in approximation theory, like the Nikolskii inequalities, which connect the norms of a function in different spaces.
So not only are these inequalities powerful on their own, but they also act as this this unifying thread, right, connecting all these different concepts and results across all these different areas of math.
Exactly. That's what makes them so fascinating to study.
Well, this deep dive it's been an incredible journey. We started with basic concepts. We explored their role in approximation theory, Nikolskii inequalities, moduli of smoothness, even embeddings of those Bezov spaces. It's amazing how far-reaching these Marcinkiewicz-Zygmund inequalities really are.
It's been a real pleasure exploring this with you.
And to our listeners, we hope you've enjoyed this deep dive as much as we have. Until next time, keep exploring, and remember, there's always something new to discover in the world of math.